Look up at the night sky on a clear evening. You see the pinpricks of light from distant stars, the soft glow of the Milky Way. It feels immense, and it is. But what you're seeing is only the tiniest fraction of the true cosmic architecture. Hidden from our eyes lies a structure of almost unimaginable scale and complexity, a vast cosmic web of galaxies strung together across billions of light years. It's the largest pattern we know of in all of existence, and for decades, one particular knot in this cosmic tapestry has defied explanation. It pulls at our galaxy and thousands of others with an irresistible, mysterious force. This is the Great Attractor, one of the universe's most profound and enduring enigmas. For years, this cosmic anomaly was a source of both fascination and frustration for astronomers. How could something so powerful exist, and why was it seemingly hidden from our view? Unraveling this mystery required more than just better telescopes. It demanded a fundamental shift in our understanding of the universe's large-scale structure. We had to learn to see the invisible threads that connect everything, to map the empty spaces as diligently as the shining beacons of light. This journey of discovery didn't just solve one puzzle. It opened the door to a deeper comprehension of how our universe is built, from the grandest superclusters down to the very fate of our own galactic home. In this video, we are embarking on a voyage to the very frontiers of cosmology. We will uncover 30 incredible secrets about the Great Attractor and the cosmic web it calls home. We will explore how dark matter weaves the universe's skeleton, how galaxies flow along hidden rivers of gravity, and how a mysterious zone of avoidance once kept the truth just out of sight. This is a story of cosmic cartography on the grandest scale, a narrative that challenges everything we thought we knew about our place in the cosmos. Prepare to have your perspective shifted as we pull back the curtain on the hidden architecture of the universe and reveal the forces that have been shaping our cosmic destiny since the dawn of time. The story of the Great Attractor begins not with a dramatic sighting, but with a subtle, nagging inconsistency in the motion of our own galaxy. In the 1970s, a team of astronomers, who would later become known as the Seven Samurai, embarked on a monumental survey of the skies. Their goal was to measure the velocities of hundreds of galaxies to create a three-dimensional map of our cosmic neighborhood. They expected to see a predictable pattern, a uniform expansion from the Big Bang where every galaxy is moving away from every other, with more distant galaxies receding faster. This is Hubble's law, the fundamental cornerstone of modern cosmology, but what they found was deeply puzzling. Our entire local group of galaxies, including the Milky Way and Andromeda, was not following the script. We were caught in a cosmic drift, a deviation from the universal expansion, as if we were being tugged sideways by an unseen hand. This peculiar motion, this unexpected velocity, was the first clue. It was like being on a raft floating down a wide, powerful river. You expect the current to carry you along in one direction, but if your raft starts steadily drifting toward one riverbank, you know there must be a secondary current, a hidden undertow pulling you off course. For the Seven Samurai, the galaxies were the rafts, and the Hubble flow was the main river. The undeniable drift indicated a gravitational undertow of staggering proportions. The initial confusion gave way to a staggering realization. The force required to pull not just our galaxy, but thousands of others along with it, had to be generated by something truly colossal, a concentration of mass equivalent to tens of thousands of Milky Ways, all located in a specific direction in the sky, toward the constellations of Centaurus and Hydra. Yet, when they pointed their telescopes in that direction, they couldn't see it. The region was largely obscured by the dusty, gas-filled plain of our own Milky Way, a zone astronomers call the zone of avoidance. It was the ultimate cosmic irony. The most significant gravitational anomaly in our local universe was hiding in our own blind spot. This only deepened the mystery. Was it a single, unimaginably dense object, a vast, unseen swarm of dark matter, or something even stranger? The discovery forced a profound admission. Our understanding of the universe's structure was incomplete. We were like mapmakers who had only charted the coastlines, suddenly realizing there was an entire, hidden continent exerting its pull on the oceans. The Great Attractor had announced its presence not with a flash of light, but with the silent, irresistible pull of gravity, rewriting the map of the cosmos from the shadows. So, just how fast are we being pulled toward this hidden anomaly? The answer is almost incomprehensible. Our Milky Way galaxy, along with our entire local group, is racing through the void at a velocity of 600 kilometers every single second. To put that into a human perspective, that's over 2 million kilometers per hour. At that staggering speed, you could travel from the Earth to the Moon in less than 11 minutes. This isn't the gentle drift of a sailboat on a calm sea. This is a bullet train velocity on a cosmic scale, an urgent, relentless rush toward a destination we couldn't initially see. This motion becomes even more remarkable when you compare it to other fundamental cosmic speeds. The Earth orbits the Sun at about 30 kilometers per second. Our entire solar system orbits the center of the Milky Way at a respectable 230 kilometers per second. Yet, this 600 kilometer per second flow toward the Great Attractor is nearly 3 times faster than our galactic orbit. It's a supervelocity, a motion that overpowers the local gravitational dances within our galaxy, indicating that its source must be something far more substantial than any structure we could see with optical telescopes. This isn't just a local curiosity, it's a dominant force in the dynamics of our entire corner of the universe. But how do we even know we're moving that fast? The key to unlocking this cosmic speedometer lies in the oldest light in the universe, the cosmic microwave background, or CMB. This faint afterglow from the Big Bang fills all of space, a nearly uniform sea of microwave radiation. Because it is the backdrop against which all other motion is measured, it serves as the universe's ultimate resting frame of reference. Imagine you're standing still in a gentle, uniform rain with the drops falling straight down on you. Now, if you start to run forward, the rain will appear to be coming at you from an angle ahead. It will feel stronger on your front. This is the Doppler effect in action. In precisely the same way, our rapid motion through space creates a wind in the cosmic microwave background. As we rush toward the Great Attractor, the microwaves coming from that direction appear slightly warmer or blue-shifted because their wavelengths are compressed by our motion. Conversely, the microwaves from the direction we're moving away from appear slightly cooler or redshifted. This creates a subtle temperature difference across the sky, a pattern known as the CMB dipole anisotropy. It's not a flaw in the cosmic background, it's our own signature of motion etched onto the oldest canvas of the universe. By meticulously mapping this temperature variation, scientists could not only confirm our incredible speed, but also pinpoint the exact direction of our travel, straight toward the heart of the hidden Great Attractor, a silent testament to the power of an unseen gravitational giant. And so, with our incredible velocity confirmed and our direction pinpointed, astronomers faced their next great challenge, actually seeing the object of our cosmic desire. The coordinates were clear, but the view was completely blocked. The Great Attractor, this gravitational titan, was located in a region of the sky that is, from our perspective on Earth, a celestial traffic jam. This is the zone of avoidance, a broad band that traces the plane of our own Milky Way galaxy. Imagine trying to see a distant mountain range, but your view is entirely obscured by a nearby, brilliantly lit and incredibly dusty city. The bright lights of the city's downtown, which are the combined glow of billions of stars in our galactic disk, blind your telescopes, and the thick smog of the city, the immense clouds of interstellar gas and dust, absorbs and scatters the visible light coming from anything behind it. For astronomers, this was the ultimate frustration. the answer to the mystery was hiding in our own backyard, concealed by the very structure we call home. This observational barrier initially brought research to a near standstill. Optical telescopes which rely on visible light were rendered almost useless. They could only see the very closest objects within the zone, the foreground stars of our own galaxy. The Great Attractor, lying far beyond this veil, was invisible. For a time, it remained a ghost known only by its gravitational influence. This led to wild speculation. Could it be an enormous black hole, a concentration of exotic matter? The inability to see it made any hypothesis seem possible. The zone of avoidance wasn't just a physical barrier, it became a psychological one, a reminder of the limitations of our earthly perspective and the tools we had relied on for centuries. But science thrives on innovation. If visible light couldn't penetrate the dust, astronomers realized they needed to listen to the universe in a different language. They turned to other parts of the electromagnetic spectrum, developing brilliant workarounds using infrared and radio telescopes. Infrared light, with its longer wavelengths, has a special property. It can pass through cosmic dust clouds that block visible light. It's like using night vision goggles to see through a haze. Space-based infrared observatories like the Infrared Astronomical Satellite and later the Spitzer Space Telescope began to peer through the zone of avoidance. They revealed thousands of galaxies that had been completely hidden, painting the first fuzzy pictures of the structures behind the murk. Even more powerful was the shift to radio astronomy. Neutral hydrogen gas, the primary ingredient of galaxies, emits a faint but distinctive radio signal at a wavelength of 21 centimeters. This signal is completely unaffected by interstellar dust. By tuning their radio telescopes to this specific frequency, astronomers could effectively hear the galaxies they couldn't see. It was a form of cosmic echolocation. They would scan the zone of avoidance, and wherever they detected a concentration of 21-centimeter radiation, they knew a galaxy was present. This technique allowed them to map the large-scale structure in the hidden zone, revealing that the Great Attractor was not a single, monstrous object, but rather the dense central core of a vast supercluster of galaxies, a gravitational nexus where the threads of the cosmic web drew together. The veil was finally lifting, not by tearing it down, but by learning to see through it. And it was this new view, this ability to peer through the cosmic veil, that led to one of the most significant revelations in the entire mystery. The Great Attractor was not what we had first imagined. It wasn't a single, monolithic entity like a hypothetical supermassive black hole or some other fantastical object. Instead, the true nature of this gravitational anomaly is both more complex and in many ways more profound. The Great Attractor is not an object at all, it is a place. Specifically, it is the gravitational heart of an immense concentration of mass, a nexus where the largest structures in the universe meet. Think of it not as a mountain peak, but as an entire mountain range. When the first detailed maps of this region were finally pieced together from infrared and radio surveys, astronomers saw a staggering tapestry of galaxies. They found that we are being drawn toward the core of what is now known as the Laniakea supercluster. Laniakea, a Hawaiian word meaning immense heaven, is an appropriately grand name for a structure that is simply breathtaking in scale. This supercluster spans over 500 million light-years and contains the mass of roughly 100,000 large galaxies, including our own Milky Way. The Great Attractor is the central gravitational valley of Laniakea, the point of deepest potential where everything in the supercluster naturally flows. Within this vast continent of galaxies, the Great Attractor represents its most densely populated metropolitan area. It's a convergence zone where several major filaments of the cosmic web, the long, thread-like chains of galaxies, intersect. At this crossroads, you find a staggering collection of massive galaxy clusters, like the Norma cluster, all bound together by their mutual gravity. This immense congregation of mass creates a gravitational well so deep that it dominates the motion of everything for hundreds of millions of light years around it. Our local group, along with the entire Virgo supercluster that we were once thought to be part of, is merely a suburb on the outskirts of this immense cosmic city, slowly sliding down the gravitational slopes toward its bustling center. This understanding transforms the Great Attractor from a mysterious thing into a fundamental feature of the universe's architecture. It is a natural consequence of the cosmic web, a gravitational focal point that formed over billions of years as dark matter guided ordinary matter into these dense nodes. The force we feel is not the pull of a single hidden monster, but the collective tug of an entire landscape of galaxies, gas, and most importantly, dark matter. This realization solved one mystery while opening up a much larger one. If the Great Attractor is just one node in the web, what lies beyond it? What even larger structure might be pulling on the Great Attractor itself, setting the entire universe in motion on a scale we are only beginning to comprehend? Now that we understand the Great Attractor as a vast gravitational center rather than a single object, we can zoom into its bustling core. The true engine of this immense pull, the heart of the gravitational anomaly, is a specific and spectacular congregation of galaxies known as the Norma Cluster. Officially catalogued as Abell Cluster 3627, this is not just any group of galaxies. It is one of the most massive and dense concentrations of matter in our entire cosmic neighborhood, lying a mere 200 million light-years away, which is practically next door on the supercluster scale. Imagine a grand central station for an entire continent of stars, with galactic trains constantly arriving and departing along cosmic filaments. The Norma Cluster is that central hub, and its gravitational influence is the primary reason we feel such a powerful tug. The composition of this cluster is what grants it such formidable gravity. It is home to several hundred galaxies, all bound together in a relatively tight space, perhaps only a few million light-years across. Within this cosmic metropolis, you find a population dominated by giant elliptical galaxies. These are not the beautiful spiral structures like our Milky Way. They are ancient, reddish, football-shaped behemoths that have grown fat through countless mergers over billions of years. They swarm around the cluster's center, where an even more immense galaxy typically resides, acting as a gravitational anchor. But the true source of the cluster's hidden mass isn't just the galaxies we can see. They are merely the visible lights of the city. The real infrastructure, the streets and foundations, is made of an enormous halo of superheated gas detected by its X-ray emissions and a truly staggering amount of dark matter. This invisible material forms a deep gravitational well that the visible galaxies simply trace, and it is this combined mass that makes the Norma Cluster a heavyweight champion of our local universe. Observational evidence firmly links this cluster to the mysterious motion of our galaxy. When astronomers finally pierced the zone of avoidance with infrared and radio telescopes, they didn't just see a few hidden galaxies. They saw the Norma Cluster in all its glory, sitting precisely in the direction of the Great Attractor's pull. By calculating the total mass of the cluster, adding up the stars, the hot gas, and the inferred dark matter, scientists could determine that its gravity is more than sufficient to account for a significant portion of our observed velocity. It acts as the central anchor of the wider Laniakea supercluster, the point where the gravitational potential is deepest. Our Milky Way, along with thousands of other galaxies, is essentially flowing down the gentle slopes of the cosmic web, converging on this dense knot. The Norma Cluster doesn't act alone. It is reinforced by other nearby clusters and groups, but it is undeniably the kingpin, the primary source of the gravitational signal we call the Great Attractor. It is the beating heart of the immense heaven we call home. This brings us to a crucial turning point in our understanding, a secret that underpins the very existence of the Great Attractor itself. We've identified the Norma Cluster as the gravitational heart, But when astronomers tallied up all the visible mass, the hundreds of galaxies, the glowing clouds of hot gas, they encountered a profound discrepancy. The numbers simply did not add up. The gravitational pull required to accelerate our galaxy to 600 kilometers per second was far greater than the combined pull of all the stars and gas we could observe. It was like calculating the force needed to hold a spinning amusement park ride together, then finding that the visible metal and bolts of the structure only accounted for a tiny fraction of the necessary strength. The unavoidable conclusion was that the true source of the Great Attractor's power is something we cannot see: dark matter. Evidence for this invisible scaffolding comes from two powerful and independent lines of astronomical detective work. The first is the study of galactic velocities within clusters like Norma. By measuring how fast individual galaxies are orbiting the cluster's center, scientists can apply the same basic principles we use to weigh the Sun by the orbits of its planets. The faster a galaxy moves, the stronger the gravitational force, and therefore the more mass must be present to hold it in place. The observed speeds of galaxies in the Norma cluster are staggeringly high, so high that if the cluster's mass came only from visible matter, those galaxies would have flown apart long ago. They are moving with a velocity that should have flung them into the void eons ago, yet they remain bound together. The only explanation is that they are trapped within an immense, invisible halo of mass, a gravitational glue holding the entire structure together. This halo, which emits no light, must be composed of dark matter, and its mass dwarfs that of all the stars and gas by a factor of about 5 to 1. The second, and perhaps even more dramatic, piece of evidence comes from a phenomenon known as gravitational lensing. This is a direct consequence of Einstein's theory of general relativity, which tells us that mass bends the fabric of space-time. A massive object acts like a lens, warping the path of light that passes near it. When we look at the region of the Great Attractor, we can sometimes see distant galaxies located far behind it. The light from these background galaxies travels through the immense gravitational field of the attractor on its way to our telescopes. Instead of seeing these distant galaxies as perfect, sharp pinpoints, we see their images subtly distorted, stretched, and magnified into faint arcs and smears. This distortion is not caused by the visible galaxies we see in the foreground. It is far too pronounced. The lensing effect reveals the true, total mass distribution of the entire region, including its dominant dark matter component. By carefully mapping these cosmic mirages, astronomers can literally chart the invisible dark matter skeleton of the Great Attractor, confirming that it is the primary architect of the gravitational landscape. This makes the Great Attractor and the Laniakea supercluster an unparalleled natural laboratory for studying dark matter. We are not just looking at a single, isolated object, but at a vast, complex ecosystem where dark matter dictates the flow of galaxies on an immense scale. By observing how galaxies move along the filaments toward the attractor and how they behave within its core, we can test theories about how dark matter interacts with itself and with normal matter. The precise way it shapes the cosmic web provides clues to its properties. Is it cold and slow-moving, or warm and a bit faster? The Great Attractor offers a real-world billion-light-year-wide experiment that we can observe, allowing us to probe the nature of the universe's most mysterious substance simply by charting the irresistible flow of everything we can see toward a point of deepest, darkest gravity. But even with the dark matter accounted for, the sheer physical dimensions of the Great Attractor are enough to defy human intuition. When we say it spans approximately 300 million light-years across, we are describing a volume of space so vast that it challenges the very meaning of the word object. To put this into a perspective we can almost grasp, consider that a single light-year is the distance light travels in 1 year, about 9.5 trillion kilometers. Now multiply that by 300 million. At the speed of light, it would take a photon, the fastest thing in the universe, 300 million years to travel from one end of this structure to the other. Our entire species has only existed for a fraction of that time. This isn't just a large cluster of galaxies, it is a continent of galaxies, a gravitational metropolis on a scale that renders our local neighborhood insignificant. A helpful comparison can be made to structures we thought were immense just a few decades ago. Our own Milky Way galaxy is a respectable 100,000 light-years in diameter. The Great Attractor is 3,000 times wider than our entire home galaxy. Even the Virgo supercluster, which we once believed contained our local group and was the largest structure we belonged to, is dwarfed. The Virgo supercluster is about 110 million light-years across. The Great Attractor complex is nearly 3 times larger, and in fact, we now understand that the Virgo supercluster is merely an appendage, a small branch on the much larger tree of Laniakea. The Great Attractor is the root system and the trunk. It's the difference between identifying your house and suddenly realizing you live in the capital city of an entire continent. Perhaps the most mind-bending aspect of its scale is how its gravitational influence extends far beyond its visible boundaries. The 300 million light-year measurement typically refers to the region containing the highest density of galaxies and dark matter, the core of Laniakea. But gravity knows no hard edges. Its pull weakens with distance, but it never truly reaches zero. This means the Great Attractor's domain of influence stretches out for hundreds of millions of light-years further, subtly steering the motion of galaxies we would consider well outside its immediate territory. Our own Milky Way, located on the far outskirts of Laniakea, is a perfect example. We are still feeling its relentless tug from a distance of 250 million light-years away. The entire Laniakea supercluster, with its hundreds of thousands of galaxies, is all part of this single, coherent river system, all flowing toward the same gravitational ocean. The true scale of the Great Attractor, therefore, is not just its physical size, but the immense volume of space over which its gravity acts as the dominant force, orchestrating the motion of galaxies across a significant portion of our observable universe. But if the Great Attractor is our primary gravitational destination, why doesn't everything in Laniakea simply collapse into its core? The answer reveals a deeper layer of cosmic motion, a secret that redefines our understanding of the universe's dynamics. The Great Attractor, as immense as it is not the final word on our cosmic journey. It is a major waypoint, a powerful local pull, but it is itself caught in an even larger and more powerful current. Our motion is not a straight fall into a single point. It is part of a vast, universe-wide river system, a phenomenon astronomers call a bulk flow. Imagine you're floating down a wide, slow-moving river toward a large lake. The current pulling you toward the lake is strong and undeniable. That's the gravitational influence of the Great Attractor. But as you get closer, you notice something extraordinary. The entire river itself is also moving, carrying the lake, you, and everything else along with it toward a colossal waterfall far downstream. This second grander motion is the bulk flow. On a cosmic scale, this means that the entire Laniakea supercluster, including the Great Attractor at its heart, is not stationary. It is being pulled en masse toward an even greater gravitational anomaly, the largest and most massive concentration of matter in our observable universe, the Shapley supercluster. The Shapley supercluster, located over 600 million light-years away in the direction of the constellation Centaurus, is a staggering megalopolis of galaxies. It contains dozens of massive galaxy clusters, making the Norma cluster seem like a modest town by comparison. Its gravitational pull is so immense that it dominates the motions of galaxies for nearly 1 billion light-years in every direction. When scientists finally mapped the peculiar velocities of thousands of galaxies, subtracting out the uniform expansion of the universe, they found a consistent pattern. Galaxies weren't just moving toward their local attractors, they were also streaming in a coherent direction toward Shapley. This revealed that the Great Attractor is not the ultimate source of our motion, but rather a middle manager in a cosmic corporate structure, answering to a CEO of unimaginable power. This concept of bulk flow transforms our view from a simple local attraction to a complex, hierarchical cosmic dance. Galaxies move within clusters, clusters orbit within superclusters, and superclusters themselves drift within these vast rivers of dark matter and galaxies. It's a universe in motion on every scale, from the spin of a single galaxy to the stately drift of entire superclusters across billions of light years. Our Milky Way's 600 km/s velocity is therefore a composite vector, a sum of many motions. Our orbit within the local group. The local groups fall toward the Virgo cluster, Virgo's trajectory toward the Great Attractor, and the entire Laniakea complexes drift toward the Shapley supercluster. We are participating in a gravitational symphony with movements spanning the entire cosmic scale. Understanding this intricate dance leads to a profound realization about the universe's structure. These bulk flows are not random, they are direct traces of the distribution of mass, especially dark matter. They allow us to map the cosmic web in 3 dimensions, not just by seeing where the galaxies are, but by watching how they move. The coherent flow toward Shapley tells us that there must be an even greater concentration of mass beyond what we have directly observed, perhaps extending into the unknown realms of the observable universe. This motion is a fossil record of the initial conditions of the Big Bang, amplified over 13.8 billion years by gravity. By studying our place in this cosmic flow, we are essentially reading the history of the universe, following the gravitational pathways that were laid down in the first moments of time, and discovering that our journey is far grander and more interconnected than we ever imagined. So, we've mapped the hidden galaxies with radio waves and inferred the presence of dark matter through its gravitational effects. But there was still a missing piece of the mass puzzle, a component of the Great Attractor that was both invisible and incredibly energetic. The key to finding it was to look not for the galaxies themselves, but for the space between them. And for that, astronomers had to turn their instruments to the most violent and energetic processes in the universe, observing in X-rays. This shift in perspective revealed that the vast voids between galaxies within clusters are not empty at all. They are filled with a seething, multimillion-degree ocean of plasma. This superheated gas is a direct consequence of the immense gravitational field of a cluster like the one at the heart of the Great Attractor. As galaxies and vast clouds of primordial gas fell into the cluster's gravitational well over billions of years, they gained tremendous speed, crashing together with incredible force. Think of it like a cosmic traffic jam happening in slow motion over eons. When these massive clouds of gas collide, they don't just gently bump. They compress and shock heat to temperatures so extreme that electrons are stripped from their atoms, creating a thin, incredibly hot soup of particles known as plasma. This plasma is so hot that it glows not in visible light, but in high-energy X-rays. From our perspective on Earth, this region behind the zone of avoidance was dark in visible light, but it was shining like a beacon in the X-ray sky. Space-based observatories like the Rosat satellite in the 1990s and later XMM Newton and Chandra were crucial for this discovery. Unlike optical or infrared light, X-rays from space are almost completely blocked by our atmosphere, so these telescopes had to be placed in orbit. When they were pointed toward the Great Attractor region, they didn't see a faint smudge. They detected a brilliant, diffuse X-ray glow. This was the signature of the hot intracluster medium, the immense reservoir of gas trapped within the gravitational grip of the Norma cluster and its surroundings. The sheer intensity of this X-ray emission was staggering, indicating a gas temperature of tens of millions of degrees Celsius. This wasn't just a wisp of warm air. It was a major component of the cluster's total mass, often containing more ordinary matter than all the stars in all the cluster's galaxies combined. The significance of this discovery cannot be overstated. First, it solved a long-standing mystery in cosmology known as the missing baryon problem. Baryons are the particles that make up ordinary matter. Protons, neutrons, and electrons, everything we see in stars, planets, and ourselves. When astronomers calculated the total amount of baryonic matter that should have been created in the Big Bang, they found that the mass locked up in stars and galaxies only accounted for a fraction of the predicted total. Where was the rest? The X-ray observations of clusters like Norma provided the answer. A huge portion of the universe's ordinary matter exists in these vast, hot reservoirs of gas between galaxies. The Great Attractor, therefore, wasn't just a source of gravitational mystery. It was a key location for accounting for the universe's ordinary inventory. Secondly, and more directly related to the attractor's pull, this hot gas provided undeniable, visible proof of the immense concentration of mass. The properties of the X-ray glow allowed scientists to precisely weigh the gas itself. By measuring the temperature and density of the plasma, they could calculate the pressure holding it up against the crushing force of the cluster's gravity. This, in turn, allowed them to calculate the total gravitational mass needed to contain such a hot, energetic atmosphere. The numbers derived from the X-ray data independently confirmed the enormous mass estimates that had been inferred from galaxy motions and gravitational lensing. It was a powerful convergence of evidence. Three different techniques: galaxy velocities, light bending, and X-ray gas, all pointing to the same colossal mass for the Great Attractor, finally bringing the invisible giant into clear focus. But to truly grasp the immense scale of this gravitational arena, we need to zoom out from the Norma cluster and explore the wider cosmic neighborhood in which the Great Attractor resides. This brings us to a crucial yet often overlooked structure, the Hydra Centaurus supercluster. Before the discovery of the even larger Laniakea, Hydra Centaurus was considered our immediate supercluster, and it remains the immediate gravitational environment that directly feeds into the Great Attractor. Think of it as the sprawling suburban county that surrounds the dense downtown core of a major city. It's a vast collection of galaxy groups and clusters, including the Hydra cluster and the Centaurus cluster, all interconnected by faint filaments of galaxies, acting as tributaries flowing into a central river. The gravitational dance between these neighboring structures is constant and complex. The Centaurus cluster, for instance, is a massive entity in its own right, located relatively close to the Norma cluster. Their gravitational fields overlap and interact, creating a dynamic tug-of-war that influences the motion of every galaxy in the region. Our own Milky Way's path is not a simple straight line to the Norma cluster. It's a curved trajectory shaped by the combined pull of all these major mass concentrations. The Hydra Centaurus supercluster doesn't just surround the Great Attractor, it actively contributes to its power. The collective mass of these neighboring clusters deepens the overall gravitational well of the region, making the attractor's pull stronger and its influence more far-reaching than it would be if it were an isolated anomaly. It's the difference between a lone mountain and an entire mountain range. The collective mass of the range defines the entire landscape. This arrangement is a perfect illustration of the hierarchical nature of cosmic structure formation, a fundamental principle of how our universe built itself. The process began with the tiniest fluctuations in the density of the early universe, slight overdensities of dark matter that acted as gravitational seeds. Over billions of years, these seeds attracted more and more matter, first forming small dwarf galaxies, which then merged into larger galaxies like our Milky Way. Gravity didn't stop there. These galaxies, in turn, were drawn together into groups like our local group. Groups then coalesced into clusters such as the Virgo cluster. And finally, clusters gathered into the vast superclusters we see today, like Hydra Centaurus and the overarching Laniakea. In this hierarchy, the Great Attractor represents a key node, a gravitational sink where several streams of this cosmic river system converge. The Hydra Centaurus supercluster is one of the major watersheds feeding this sink. The filaments of galaxies that make up Hydra Centaurus are like rivers slowly draining into a great lake. This hierarchical model explains why the universe isn't a uniform soup of galaxies. Instead, it's a web of voids, walls, filaments, and nodes with structure on every scale. The Great Attractor is not an exception to the rules of cosmology. It is a textbook example of those rules operating on the grandest possible stage, showing us how gravity, given enough time, can sculpt a smooth primordial universe into the intricate and magnificent cosmic web we observe today. So, we know the Great Attractor is there because of its gravitational pull, and we've even glimpsed its core through X-rays and radio waves. But to truly see it for what it is, a vast, three-dimensional structure in the cosmic web required a different kind of astronomical revolution. Astronomers needed to move beyond studying individual objects and instead launch a grand campaign of cosmic cartography. This monumental task was accomplished through massive redshift surveys, projects of almost unimaginable ambition that systematically mapped the positions and distances of millions of galaxies across the sky. These surveys, like the 2-degree field galaxy redshift survey and the Sloan Digital Sky Survey, didn't just give us a better picture, they gave us the very first three-dimensional atlas of our universe on the largest scales. The key to this mapping lies in a simple but powerful concept: redshift. When a galaxy is moving away from us, the light waves it emits get stretched out, shifting toward the red end of the spectrum. The faster the galaxy is receding, the greater this redshift. Because the universe is expanding, more distant galaxies are moving away from us faster than nearby ones. This means a galaxy's redshift acts as a direct measure of its distance from Earth. By pointing a telescope at a galaxy, splitting its light into a spectrum, and measuring how much its characteristic light signatures have shifted to the red, astronomers can calculate not just how fast it's moving, but precisely how far away it is. It's a universal distance marker, a gift from the physics of the expanding universe. Before these large surveys, measuring redshift was a painstaking, one galaxy at a time process. The new surveys changed everything by using sophisticated fiber optic systems that could capture the light from hundreds of galaxies simultaneously, turning a slow trickle of data into a fire hose. When the data from these surveys was finally processed and visualized, the result was nothing short of breathtaking. Instead of seeing a random scattering of points, a profound architecture emerged. Galaxies were organized into an intricate web-like pattern, with long, dense filaments and massive clusters interconnected across vast distances. And between these structures lay immense, nearly empty regions, cosmic voids spanning hundreds of millions of light years. In this revolutionary three-dimensional map, the Great Attractor was finally revealed in its full context. It was not an isolated anomaly, but the most prominent density peak in our entire local universe, the place where several major filaments of the cosmic web intersected. It was the glittering nodal point in a sprawling cosmic network. The maps made the existence of the voids just as important as the clusters themselves. These are not merely empty space, they are regions of profoundly low density, containing very few galaxies and an even lower concentration of dark matter. The sculptor void and the local void are two such enormous empty regions that border our own local group of galaxies. Understanding these voids was critical to solving the mystery of our motion. Think of the cosmic web as a range of mountains and valleys, but where gravity works in reverse. In this landscape, the dense clusters like the Great Attractor are the gravitational valleys, the low points where matter collects. The voids, by contrast, are the gravitational hills. Because they have so little mass, they exert very little gravitational pull. This creates an imbalance. The strong pull from the dense region combined with the weak push from the empty region effectively gives galaxies a net shove toward the mass. Our journey toward the Great Attractor is in part a slide down a gravitational slope away from the emptiness of the local void. The redshift surveys showed us that we live in a universe of extremes, where the great empty spaces work in concert with the great concentrations of matter to orchestrate the motion of everything within it. This brings us to a concept that might seem counterintuitive, a secret that balances the immense pull of the Great Attractor with an equally powerful push. For decades, we've focused on the tug of massive structures, but the universe is a tapestry woven from both dense clusters and profound emptiness. The full explanation for our 600 km/s journey requires us to understand not just what is pulling us, but also what is pushing us away. This is the mystery of the dipole repeller. Imagine you're in a boat on a calm lake. If you want to move the boat, you can either row towards something or you can push off from the dock behind you. In the cosmic sense, the Great Attractor is the destination we're rowing toward, but the dipole repeller is the dock we're pushing away from. It is not an object with anti-gravity, but rather a vast and exceptionally empty region of space, a cosmic void so underdense that its lack of gravitational pull creates an effective repulsive force. The logic behind this is rooted in the very nature of gravity and the large-scale structure of the universe. Gravity is always attractive, it never pushes. So how can something repel? The answer lies in the principle of imbalance. Our local group of galaxies exists in a neighborhood that is not uniform. On one side, we have the immense gravitational valley of the Great Attractor. On the opposite side, in the direction we are moving from, astronomers have identified an enormous volume of space that is strikingly empty. This is the dipole repeller. Because this region contains far less matter than the cosmic average, its gravitational pull is exceptionally weak. In the grand tug of war that dictates cosmic motion, the strong pull from the dense attractor combined with the exceptionally weak pull from the empty repeller creates a net effect. It's as if the rope has gone slack on one side. The result is that we are not so much pulled toward the attractor as we are pushed away from the void, sliding down the gravitational gradient from a hill of nothingness into a valley of everything. Recent research, particularly a groundbreaking study published in 2017, used sophisticated computer models and velocity maps of thousands of galaxies to quantify the influence of this repeller. The scientists found that to accurately explain the observed motion of our galaxy and our local supercluster, they had to account for the gravitational influence of both the overdensities, like the Shapley supercluster and the Great Attractor, and the underdensities, the voids. Their models revealed that the dipole repeller contributes just as much to our peculiar velocity as the combined pull of the Great Attractor and its surrounding structures. This was a paradigm shift. It showed that cosmic flows are not dictated solely by the glittering cities of galaxies, but are equally orchestrated by the vast, dark countryside of empty space. The emptiness itself is an active player in shaping the architecture and dynamics of the universe. This understanding transforms our view of the cosmic web from a simple map of where things are to a dynamic picture of how things move. The Great Attractor and the dipole repeller are two sides of the same gravitational coin. One is a concentration of mass that draws matter in, the other is a deficit of mass that allows matter to flow away. They work in concert, creating the currents that guide galaxies across billions of light years. This dance between the something and the nothing is a fundamental feature of our universe, a reminder that what is absent can be just as influential as what is present. By acknowledging the push of the void, we complete the picture of our cosmic journey, understanding that we are navigated by the gravity of both the seen and the unseen, the full and the empty. To truly map the invisible architecture of the Great Attractor, astronomers needed a reliable way to chart its structure. They couldn't simply count every single galaxy. The task would be monumental and the resulting map overly complex. Instead, they turned to a powerful shortcut, using the largest and most massive gravitationally bound objects in the universe as signposts. These are the galaxy clusters, and they serve as near-perfect tracers for the underlying cosmic web. Think of it like trying to map a continent at night. You wouldn't need to see every house and street. By locating the brightest, largest cities and the major highways that connect them, you can accurately outline the entire civilization. In the darkness of space, galaxy clusters are those brilliant metropolitan areas, and their distribution reveals the hidden superstructure of the Great Attractor. Finding these clusters, however, especially ones hidden behind the zone of avoidance, requires a multi-wavelength toolkit. One of the most effective methods relies on the intense X-ray glow we discussed earlier. When a galaxy cluster forms, vast amounts of gas fall into its gravitational well and are heated to extreme temperatures. This makes the entire cluster shine brightly in X-rays, often outshining the combined light of all its member galaxies. For a cosmologist, an X-ray telescope acts like a pair of heat vision goggles, allowing them to scan the sky and instantly spot these colossal, energetic objects. A bright, extended patch of X-ray emission is almost always the signature of a massive cluster. This technique is incredibly efficient because it doesn't depend on seeing individual galaxies. It detects the cluster's main reservoir of ordinary matter directly. Surveys like the Ross et al. Sky Survey provided the first complete X-ray map of the sky, revealing the locations of thousands of clusters, including many previously unknown ones in the direction of the Great Attractor, painting a vivid picture of its hot, gaseous skeleton. But X-rays are only part of the story. To confirm a candidate cluster and understand its properties, astronomers cross-reference the data with observations in optical and infrared light. They point large telescopes at the coordinates of an X-ray source and take a deep image. If the X-ray emission is genuine, they will see a dense congregation of hundreds or even thousands of galaxies all clustered together in the same small patch of sky. The sheer concentration of galaxies in one spot is a dead giveaway. By then measuring the redshifts of these galaxies, they can confirm that they are all at the same distance, physically bound together, and not just a chance alignment along our line of sight. This combined approach, X-rays to find the hot gas and optical observations to count the galaxies, provides a robust way to identify and weigh these colossal structures, building a census of the major mass concentrations within the Great Attractor region. The most profound confirmation of a cluster's mass, however, comes from its effect on the fabric of space-time itself, gravitational lensing. This phenomenon provides a direct way to measure the total mass, including the all-important dark matter, without relying on the light emitted by the cluster. When light from a distant galaxy passes near a massive cluster, its path is bent by gravity, creating distorted, stretched, and sometimes multiple images of the background object. The strength of this lensing effect is directly proportional to the total mass of the cluster doing the lensing. By carefully analyzing these cosmic mirages, astronomers can create a mass map of the foreground cluster. When they apply this technique to the clusters in the Great Attractor, the results are striking. The lensing maps reveal that the visible galaxies and hot gas are merely the tip of the iceberg, sitting at the center of a much larger, invisible halo of dark matter. This dark matter halo is the true source of the gravitational power that defines the attractor, and its shape often extends along the invisible filaments of the cosmic web, showing the direct pathways of mass that feed the great cluster. By compiling the locations of hundreds of clusters using these techniques, a stunning pattern emerges. The clusters are not scattered randomly. They line up along specific, faint pathways, tracing the filaments of the cosmic web that converge on the Norma cluster, the heart of the Great Attractor. The distribution of these clusters acts as a three-dimensional blueprint for the underlying dark matter distribution. Where clusters are densely packed, the dark matter is densest. The empty spaces between these cluster-lined filaments correspond to the great cosmic voids. This map of clusters is therefore a map of the gravitational potential of the entire region. It shows us precisely where the gravitational hills and valleys are, explaining exactly why thousands of galaxies, including our own, are flowing along these hidden topographical lines toward the deepest valley of them all. The galaxy clusters are the luminous markers that have allowed us to finally see the full, magnificent scale of the gravitational landscape that has been guiding our cosmic destiny for billions of years. This concept of the Great Attractor as a central node leads us directly to the grandest architectural blueprint of the cosmos, the cosmic web. To truly appreciate its role, we need to visualize the universe not as a random scattering of galaxies, but as an immense three-dimensional network. This web is spun from three primary structures: the dense clusters and superclusters that form the nodes, the long, thread-like filaments that connect them, and the vast, empty voids that separate them. It's a structure that mirrors a sponge or a collection of soap bubbles, where the galaxies cling to the surfaces of the bubbles and the interiors are nearly empty space. The Great Attractor is not merely a feature within this web. It is one of its most prominent and powerful intersections, a gravitational crossroads where the universe's largest highways meet. The filaments are the true backbone of this structure. These are colossal rivers of dark matter, hundreds of millions of light-years long, but only a few million light-years wide, along which galaxies are strung like pearls on a necklace. They act as the universe's transportation system, funneling gas and galaxies from the empty voids toward the dense clusters. The Great Attractor sits at the convergence of several of these major cosmic filaments. One of the most significant is the filament extending from the Perseus-Pisces supercluster, another immense wall of galaxies. Another flows in from the direction of the Shapley supercluster, and yet another connects it to our own local filamentary structure. It is this convergence that creates the extraordinary gravitational deep well we experience. The attractor is the cosmic equivalent of a major railway hub, like Grand Central Terminal, where multiple train lines converge, bringing a constant flow of traffic to a central location. Surrounding these filaments are the even larger scale structures known as walls or sheets. These are vast, flattened concentrations of galaxies that can stretch for over 1 billion light-years but are relatively thin, like colossal cosmic membranes. The Great Attractor forms a part of what some cosmologists call the Centaurus Wall, a broad sheet of galaxies that includes the Hydra Centaurus supercluster. This wall is itself one of the boundaries of an even greater void. This interplay between wall, filament, and node creates a complex gravitational landscape. The walls provide the broad plains, the filaments are the mountain ridges, and the nodes, like the Great Attractor, are the deepest valleys. Galaxies naturally flow from the high ground of the voids, down the ridges of the filaments, and into the gravitational valleys of the clusters. The existence of this web is a direct prediction of our leading model of cosmic evolution, known as the lambda cold dark matter model. According to this model, the seeds of the web were planted in the first infinitesimal fraction of a second after the Big Bang, as microscopic quantum fluctuations were stretched to cosmic size during a period of rapid inflation. Over the ensuing 13.8 billion years, gravity acted as the master sculptor. The slightly denser regions, dominated by dark matter, began to attract more and more matter. The dark matter formed an invisible scaffolding, and ordinary matter, the gas that would eventually form stars and galaxies, flowed along this pre-existing framework, settling into the filaments and nodes we observe today. The Great Attractor, therefore, is a fossil from the dawn of time, a structure whose location and immense power were dictated by the initial conditions of the universe itself. Understanding the Great Attractor as a web node fundamentally changes our perspective on its influence. Its gravity is not just a local force pulling on nearby galaxies. It governs the flow of matter along entire filamentary pathways for hundreds of millions of light-years. The motion of our Milky Way is part of this larger circulation pattern. We are not simply falling toward a point, we are flowing along a cosmic river, a current defined by the web's architecture. This web-centric view also reveals that the Great Attractor is not unique. Throughout the observable universe, there are other similar nodal points, other grand central stations where filaments meet. But for us, it is the most significant, the dominant knot in the cosmic tapestry that defines our immediate cosmic environment and our long-term trajectory through the universe. Now that we understand the grand stage of the cosmic web, we can focus on the precise instruments that allowed astronomers to measure our place upon it. This brings us to the heart of observational cosmology, the meticulous science of measuring peculiar velocities. This term, peculiar velocity, might sound like a scientific oddity, but it describes a fundamental concept. It is the real, physical motion of a galaxy through space, over and above the simple expansion of the universe described by Hubble's law. Think of it this way. If the universe's expansion is like the current of a wide, slow-moving river carrying all boats along, then a galaxy's peculiar velocity is the speed and direction at which that boat is actively sailing relative to the current. For our Milky Way, that peculiar velocity is the 600 kilometers per second rush toward the Great Attractor, a motion that exists independently of the cosmic expansion. Separating this peculiar motion from the Hubble flow is a monumental challenge, akin to trying to measure the exact speed of a car on a moving train by only looking out the window at the passing landscape. The first and most critical step is to determine a galaxy's true distance with as much precision as possible. Hubble's law gives us a predicted velocity based on distance. The farther away a galaxy is, the faster it should be receding from us. But this only works if the galaxy is far enough away that its local gravitational interactions are negligible compared to the cosmic expansion. For nearby galaxies, like those within a few 100 million light-years, their peculiar velocities can be a significant fraction of their Hubble flow velocity, muddying the waters entirely. So, astronomers need independent distance measurements that don't rely on redshift. This is where the cosmic distance ladder comes into play. Astronomers use a series of techniques, each calibrated by the one before it, to climb from nearby stars to distant galaxies. For relatively close galaxies, the most reliable standard candles are Cepheid variable stars. These stars pulsate with a regular rhythm, and the period of their pulsation is directly related to their intrinsic brightness. By measuring the pulsation period, astronomers know the star's true luminosity. Comparing this known brightness to how dim the star appears from Earth gives a precise measurement of its distance. Space telescopes like Hubble have been indispensable for identifying Cepheids in other galaxies, providing a solid foundation for the distance ladder. Another crucial standard candle is the Type Ia supernova, a thermonuclear explosion of a white dwarf star that always reaches a known peak brightness. These cosmic beacons are so brilliant they can be seen across billions of light-years, allowing astronomers to measure distances to far-off galaxies with remarkable accuracy. Once an independent distance is established, the detective work can begin. Astronomers then measure the galaxy's redshift, which tells them the galaxy's apparent recessional velocity due to the expansion of the universe. They then compare this observed velocity to the velocity predicted by Hubble's law based on the independently measured distance. The difference between the two is the galaxy's peculiar velocity. If the observed velocity is greater than the Hubble prediction, the galaxy has an additional velocity away from us. If it's less, the galaxy is moving toward us. By plotting the peculiar velocities of thousands of galaxies across the sky, a stunning map of cosmic flows emerges, revealing the invisible gravitational landscape of our local universe with all its attractors and repellers. Modern technology has revolutionized this process. Instead of studying galaxies one by one, astronomers now conduct massive redshift surveys using instruments that can capture the spectra of hundreds or even thousands of galaxies simultaneously. Projects like the Sloan Digital Sky Survey have provided a rich dataset of positions and redshifts for millions of galaxies. When combined with ever more precise distance measurements from new observatories like the Gaia spacecraft, which is mapping the positions and motions of stars within our own galaxy with unprecedented accuracy, we are entering a golden age of precision cosmology. These vast datasets allow scientists to run sophisticated computer models that simulate the gravitational influence of all the known matter, both visible and dark, in our local universe. The models predict what the peculiar velocities should be, and by comparing these predictions to the actual, painstakingly measured velocities, astronomers can test and refine our understanding of the large-scale structure, effectively using the motion of galaxies to weigh the cosmos and confirm the overwhelming gravitational dominance of the Great Attractor and the vast cosmic web it calls home. So, with our trajectory mapped and our destination clear, we are left with a profound question about our cosmic fate. What does the future hold for our journey toward this gravitational titan? Will our local group of galaxies eventually merge into the bustling core of the Great Attractor, becoming just another star in its glittering metropolis? The answer is a fascinating paradox, a cosmic race between two fundamental forces that have shaped the universe since the beginning. While the pull of gravity is relentless, there is another, even more powerful player in this drama: the accelerated expansion of the universe, driven by the mysterious force known as dark energy. Calculating our future path requires modeling this intricate tug-of-war. On one hand, gravity is constantly working to pull us closer. Based on our current velocity and distance, if the universe were static, we would indeed be on a collision course. The math would be straightforward: distance divided by speed. Given we are roughly 250 million light-years away and moving at 600 kilometers per second, a simple calculation suggests we might reach the vicinity of the Great Attractor in a few tens of billions of years. But the universe is not static, it is stretching, and that expansion is not just a background effect, it is actively working against gravity's pull. This is where dark energy becomes the deciding factor. Observations of distant supernova in the late 1990s revealed a shocking truth. The expansion of the universe is not slowing down due to gravity, as everyone had assumed. Instead, it is speeding up. Some repulsive force, now called dark energy, is causing space itself to stretch at an ever-increasing rate. On the very largest scales, this expansion dominates. Think of it like trying to swim toward a dock on a river that is flowing faster and faster. Even if you are a strong swimmer headed directly for the dock, if the current accelerates enough, you may find yourself being carried downstream, never reaching your goal. In our cosmic analogy, dark energy is that accelerating current of space itself. The most recent and sophisticated models of our local universe now paint a clear, if counterintuitive, picture of our destiny. They show that while the Great Attractor will continue to pull us closer for many billions of years, the overall expansion of the universe will ultimately win the race. We will approach the attractor, but we will never actually join it. Our local group will reach a point of closest approach, a perihelion on a galactic scale. And then, as the expansion between us and the attractor continues to accelerate, we will begin to slowly drift away. The Great Attractor will eventually fade into the distance, becoming just one of many receding galaxy clusters in an ever more isolated universe. This outcome is a direct consequence of the different scales at which gravity and dark energy operate. Gravity is strongest locally, binding galaxies into clusters and governing the motion within superclusters like Laniakea. This is why we are flowing toward the attractor now. But dark energy acts uniformly across the vast emptiness of cosmic voids. As the universe ages, these voids grow larger and emptier, and the influence of dark energy increases. Over time, the gravitational bonds that hold superclusters together will be overcome. The cosmic web itself will be stretched apart, with the filaments stretching and eventually snapping. Galaxies in the far future will find themselves isolated in an immense, dark, and ever-expanding void, their collective past as members of a great supercluster just a fading memory. Our journey toward the Great Attractor is therefore a temporary phase, a grand multi-billion-year arc that defines our current cosmic epoch, but not our eternal fate. But if the cosmic web is the finished architecture, how did it get there? How did a universe that began in a near-perfectly smooth, hot state evolve into the intricate tapestry of walls, filaments, and clusters we see today? The story of the Great Attractor's formation is not just about its current location. It's a journey back to the first fleeting moments after the Big Bang. The leading theories that explain this incredible transformation hinge on three key ingredients: a mysterious repulsive force that set the stage, an invisible scaffolding that dictated the blueprint, and tiny quantum whispers that provided the raw material. This is the story of cosmic structure formation, a process that turned uniformity into complexity over billions of years. It all starts with inflation, a concept that is as radical as it is essential. In the first fraction of a second after the universe's birth, space itself underwent a period of exponentially rapid expansion, inflating from a subatomic scale to something much larger than our entire observable universe in a span of time too short to comprehend. This inflationary epoch did more than just make the universe big. It made it incredibly smooth and flat. However, due to the quantum nature of reality, this process wasn't perfectly uniform. On the smallest scales, quantum fluctuations, tiny, random variations in energy, were inevitable. As space inflated at a staggering rate, these microscopic fluctuations were stretched to astronomical sizes. What were once quantum jitters became macroscopic variations in the density of the universe. These minute differences on the order of 1 part in 100,000 became the seeds for all future structure. The denser regions held slightly more mass and thus slightly stronger gravity. They were the primordial blueprints for every galaxy cluster, every supercluster, and ultimately for the Great Attractor itself. Without inflation's magnification of these quantum seeds, the universe might have remained a featureless soup forever. After inflation ended, the universe was filled with a hot, dense plasma of particles and radiation. For hundreds of thousands of years, radiation pressure was so intense that it prevented matter from clumping together. Gravity was trying to pull the slightly denser regions together, but the force of light pushing outward kept everything mixed. This changed at a pivotal moment known as recombination, when the universe had cooled enough for electrons to combine with protons to form neutral atoms. Suddenly, the universe became transparent to light. The radiation, which we now detect as the cosmic microwave background, decoupled from matter and streamed freely across space. With the radiation pressure gone, gravity was finally free to go to work. This is the moment the cosmic construction project began. The tiny density variations imprinted by inflation were now frozen into the distribution of matter, and gravity began to amplify them relentlessly. This is where the true hero of the story, dark matter, enters the scene. Ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and us, was still under pressure from the leftover radiation. But dark matter, which does not interact with light or other forces, felt no such pressure. It was able to start collapsing into gravitationally bound structures much earlier than ordinary matter. Think of dark matter as the invisible framework of a building and ordinary matter as the bricks and mortar. The dark matter formed an intricate web of filaments and halos first, creating a gravitational landscape of hills and valleys. Then, after recombination, the ordinary matter simply flowed into the pre-existing gravitational wells carved out by the dark matter. The Great Attractor began not as a collection of shining galaxies, but as a particularly dense knot in the dark matter web that formed early on, drawing in vast amounts of gas that would later fragment into the galaxies we see today. We can witness this entire process unfold through the power of supercomputer simulations. Cosmologists input the known laws of physics. the measured initial conditions from the cosmic microwave background, and the estimated amounts of dark matter and dark energy. They then let the simulation run, watching as virtual universes evolve over billions of years. The results are breathtakingly accurate. These simulations consistently produce a cosmic web that looks almost identical to the one mapped by our telescopes. They show how small density fluctuations grow through gravitational instability, how dark matter forms a cosmic skeleton, and how gas cools and condenses to form galaxies along the filaments. When scientists focus on a simulated volume of space equivalent to our local universe, a structure remarkably similar to the Laniakea supercluster and the Great Attractor naturally emerges. The simulations don't program in a Great Attractor. They show that given the initial conditions and the laws of physics as we understand them, a structure of its scale and mass is a natural, expected outcome. This provides powerful confirmation that our theories about the universe's infancy and its invisible components are on the right track. The final piece of the puzzle involves understanding the specific type of dark matter. The prevailing model, known as cold dark matter, assumes the particles moved slowly in the early universe. This cold nature is crucial because it allows structures to form from the bottom up. Small dwarf galaxies form first and then merge hierarchically to build larger galaxies, clusters, and superclusters. This bottom-up scenario perfectly explains the web-like structure we observe. If dark matter were hot or fast-moving, it would have smoothed out those small-scale initial fluctuations, leading to a top-down formation where large sheets fragmented into galaxies, a pattern that doesn't match our observations. The existence of a well-defined, dense node like the Great Attractor, fed by clear filaments, is a strong argument in favor of the cold dark matter model. It tells us that the invisible substance shaping our cosmos is slow-moving and clumpy, providing the granularity needed for gravity to build the universe's magnificent large-scale architecture, piece by piece, over billions of years. To truly measure the grand architecture of the cosmos, from the filaments feeding the Great Attractor to the voids that push us away, astronomers needed a ruler of cosmic proportions. They needed a standard measuring stick, one that was imprinted on the universe at its birth and remains visible billions of years later. This brings us to one of the most elegant and powerful tools in modern cosmology, baryonic acoustic oscillations, or BAO. Think of them as fossilized sound waves from the early universe, providing a permanent ruler etched into the very distribution of matter. These oscillations are not just a curious relic, they are the fundamental tool that allowed us to precisely map the scale of the cosmic web, confirming the immense size of structures like Laniakea and providing an independent check on the dark energy that will ultimately determine our fate. The story of BAOs begins in the first few 100,000 years after the Big Bang, when the universe was a seething, opaque plasma. Ordinary matter, which scientists call baryonic matter, was a soup of protons and electrons, and it was coupled with light photons were constantly bouncing off the charged particles, creating immense radiation pressure. In this hot, dense environment, gravity was already at work, trying to pull the slightly denser regions of dark matter together. But when gravity tried to pull the baryonic matter into these dark matter wells, it ran into a problem: the photon pressure pushed back. This created a tug of war, with gravity pulling matter in and radiation pressure pushing it out. The result was a series of spherical sound waves or pressure waves that rippled outward through the plasma, much like the ripples from a stone dropped in a pond. These sound waves traveled at an incredible speed, roughly half the speed of light, for about 380,000 years. Then, at the moment of recombination, when the universe cooled enough for atoms to form and become transparent, something crucial happened. The photons suddenly stopped pushing. They decoupled from the matter and streamed freely across space, becoming what we now observe as the cosmic microwave background. Instantly, the pressure support for the sound waves vanished. The waves froze in place, leaving behind a distinct signature, spherical shells of matter that had been carried outward by the pressure wave. Each initial overdensity became surrounded by a shell of slightly higher density at a very specific distance, the distance the sound wave had traveled before it stopped. This distance became a standard ruler, a fixed measuring stick imprinted on the universe. When we look at the universe today, we can still see this imprint. It manifests as a subtle preference for galaxies to be separated by a specific distance, which corresponds to that frozen sound wave scale. In the large-scale structure maps created by surveys like the Sloan Digital Sky Survey, when astronomers measure the distances between hundreds of thousands of galaxy pairs, they find a small but statistically significant excess of pairs separated by about 500 million light-years. This is not a coincidence, it is the direct descendant of those ancient acoustic oscillations. The BAO scale acts as a cosmic ruler that has expanded along with the universe itself. We know its original size from the physics of the early universe, and by measuring its apparent size in the sky at different epochs, both in the nearby universe and in the very distant past, we can measure how the expansion of the universe has stretched over time with extraordinary precision. For mapping the Great Attractor and its surrounding supercluster, BAOs provided a critical reality check. By using this fixed ruler, astronomers could measure the true physical size of Laniakea without relying on the more complex and potentially error-prone methods of the cosmic distance ladder. The BAO signal confirmed that the vast web of filaments and nodes spanning hundreds of millions of light-years was real and that its dimensions were consistent with our gravitational models. It helped to calibrate the peculiar velocities of galaxies, providing an independent frame of reference to understand how much of their motion was due to the Hubble flow and how much was due to the local gravitational pull of structures like the Great Attractor. In essence, BAOs gave us a stable, universal grid against which we could chart the dynamic flows of galaxies, separating the calm expansion of space from the violent gravitational currents that shape our immediate cosmic environment. Perhaps the most profound application of baryonic acoustic oscillations, however, has been in the study of dark energy. Because the BAO ruler is fixed and its apparent size changes with the expansion history of the universe, it serves as a direct probe of how that expansion rate has changed over billions of years. By measuring the BAO scale in the distribution of extremely distant galaxies, we look back in time to when the universe was younger. Comparing that to the BAO scale in the local universe tells us how much the universe has stretched in the intervening eons. These meticulous measurements have provided some of the strongest independent confirmation for the accelerated expansion driven by dark energy. They show us that the cosmic web is not only a structure of the past but also a key to understanding the future fate of all structure, including the eventual dissolution of the great gravitational bonds that hold the Great Attractor together. We've explored how ancient sound waves left a ruler in the galaxy distribution, but the universe left another, even more fundamental, imprint that connects directly to the gravity of the Great Attractor. This evidence comes from the very first light, the cosmic microwave background. While the CMB is famously uniform, serving as a perfect backdrop to measure our motion, it also holds subtle secondary distortions. These tiny imperfections are not flaws, they are a treasure trove of information, a kind of cosmic forensic evidence revealing the interaction between this primordial light and the massive structures that formed later, like the Great Attractor. It's a direct link between the universe's infancy and its present-day large-scale architecture. One of the most powerful ways this connection manifests is through a phenomenon known as the kinetic Sunyaev-Zeldovich effect. To understand this, let's first recall the regular Sunyaev-Zeldovich effect, which occurs when CMB photons travel through the superheated gas of a galaxy cluster. The hot electrons in this gas give the low-energy CMB photons a slight boost in energy, effectively creating a small, shadowy imprint on the CMB map corresponding to the cluster's location. The kinetic version of this effect is more subtle and more dynamic. It doesn't rely on the temperature of the gas but on its motion. When an entire galaxy cluster is moving rapidly through space caught in a bulk flow toward a great attractor, the CMB photons that scatter off the electrons in that cluster's gas get a slightly different imprint depending on whether the cluster is moving toward us or away from us relative to the overall expansion of the universe. Detecting this effect is an exercise in extreme precision. It creates a minute temperature shift in the CMB in the direction of the moving cluster, a tiny patch of sky that appears very slightly warmer or cooler than the surrounding background. This signal is incredibly faint, often measured in millionths of a degree, but for cosmologists it's like finding a fingerprint at a crime scene. By carefully analyzing these minute distortions across the sky, particularly in the direction of the Great Attractor, astronomers can do something remarkable. They can trace the bulk flow of galaxy clusters. They can measure not just that a cluster is there, but the direction and speed at which it is traveling through space, confirming that entire groups of clusters are being swept along by the same large-scale gravitational currents that are pulling our own galaxy. This technique provides a crucial, independent line of evidence that complements optical and X-ray observations in a powerful way. Optical surveys tell us where the galaxies are. X-ray observations tell us about the hot gas within clusters, allowing us to estimate their mass. But the kinetic Sunyaev-Zeldovich effect tells us about the motion of that gas through the fundamental reference frame of the universe. It directly probes the peculiar velocities induced by the gravitational landscape. When the velocities measured from galaxy redshifts align with the velocities inferred from the CMB distortions, it gives us tremendous confidence that our models of the cosmic web are correct. It confirms that the Great Attractor is not just a static concentration of mass, but an active engine, a gravitational pivot point that is setting hundreds of galaxy clusters in motion. The true power of this connection lies in its ability to map the invisible. Because the effect is sensitive to the motion of all the hot electrons in a cluster's gas, it is effectively weighing the entire structure, including the dark matter that governs its movement. A large bulk flow detected via the kinetic Sunyaev-Zeldovich effect implies a powerful gravitational source. By combining this data with gravitational lensing maps and galaxy velocity surveys, scientists can create a three-dimensional, dynamic model of the gravitational fields in our local universe. This multi-messenger approach, using light from the birth of the universe to study structures that formed billions of years later, closes the loop on the story of the Great Attractor. It shows us that the whispers of the Big Bang are still echoing through the cosmos, carrying encoded information about the dark matter valleys and the mighty rivers of galaxies that define our place in the immensity of space. To place the Great Attractor in its proper context, we must first understand the cosmic hierarchy it belongs to. Galaxies are not scattered randomly, they organize themselves into a vast, structured system. The smallest gravitationally bound systems are groups, like our own local group, containing a few dozen galaxies. These groups then gather into clusters which can host hundreds or even thousands of galaxies, such as the Virgo cluster. But the story doesn't end there. Clusters themselves are part of something far grander, superclusters. These are the largest known structures in the universe that are still connected by gravity, immense continents of galaxies that can span hundreds of millions of light years. They are not tightly bound like a cluster. Instead, they represent a vast collection of groups, clusters, and individual galaxies that are all moving together within a shared gravitational landscape, flowing along the filaments of the cosmic web. The Great Attractor is not itself a supercluster, it is the gravitational heart of one. For a long time, we believed our home supercluster was Virgo, named for the large cluster at its center. But with more precise mapping, astronomers realized this was a misclassification. The Virgo cluster is just one of many clusters that are all falling toward a common center of gravity. In 2014, a team of scientists led by Brent Tully unveiled a new map that redefined our cosmic address. Using the peculiar velocities of thousands of galaxies, they traced the flow lines of the cosmic web, revealing the true extent of our home. They named it Laniakea, the immense heaven. This supercluster is an enormous collection of about 100,000 galaxies, stretching over 500 million light-years. At its dynamical center, the point toward which every galaxy in Laniakea is flowing, lies the Great Attractor. So, the attractor is the core gravitational anchor of the Laniakea supercluster, the deepest valley in our local cosmic terrain. Comparing Laniakea to other known superclusters helps us appreciate the scale and significance of our gravitational home. The Shapley supercluster, located about 650 million light-years away, is often considered the most massive concentration of matter in our observable universe. It's a true titan, a dense amalgamation of several dozen massive galaxy clusters. If Laniakea is a vast continent, Shapley is a supercontinent, a gravitational behemoth whose pull influences the motion of galaxies across nearly 1 billion light-years. Our entire Laniakea supercluster, including the Great Attractor, is part of a larger bulk flow being drawn toward Shapley. On the other end of the scale, the Perseus-Pisces supercluster is another immense wall of galaxies, a long, filamentary structure that acts as a major neighboring watershed to Laniakea. Each supercluster has its own unique shape and density, a testament to the varied ways gravity has sculpted the universe from the initial seeds of the Big Bang. The very definition of a supercluster hinges on this concept of a shared velocity field, a common flow. Unlike a galaxy cluster, which is a virialized object where galaxies are orbiting a common center in a stable configuration, a supercluster is still dynamically evolving. The galaxies within it have not yet settled into a neat orbital dance. Instead, they are all participating in a coherent drift toward the densest region. This is why mapping superclusters required measuring peculiar velocities, not just positions. You have to see how the galaxies are moving to understand which ones belong to the same gravitational watershed. The boundaries between superclusters are not sharp lines but rather gravitational divides, like continental divides on Earth where water flows toward different oceans. Laniakea's border is defined by the points where the flow of galaxies switches direction, no longer heading toward the Great Attractor but toward a different gravitational center, like the Perseus-Pisces or Shapley superclusters. This hierarchical structure, from groups to clusters to superclusters, represents the very largest scale at which matter is still coherently connected. Beyond superclusters, the accelerating expansion of the universe, driven by dark energy, begins to dominate. The gravitational bonds that define Laniakea will, over tens of billions of years, be stretched and eventually torn apart by this cosmic expansion. For now, however, superclusters represent the pinnacle of cosmic architecture, the final chapter in the story of structure formation. They are the ultimate expression of gravity's persistent work over 13.8 billion years, gathering matter from the smooth early universe into these magnificent continent-scale tapestries. The Great Attractor, as the core of Laniakea, is therefore a key landmark in our local universe, a central node that not only defines our motion, but also helps us understand the limits of gravitational cohesion in an ever-expanding cosmos. Within the immense gravitational dominion of the Great Attractor, the dense galaxy clusters like Norma are far more than just landmarks. They are violent cosmic crucibles where galaxies are forged and fundamentally transformed. While the serene spiral of our own Milky Way evolves in the relative quiet of the galactic suburbs, a galaxy falling into the heart of the Great Attractor enters a hostile and extreme environment. The space between galaxies here is not empty. It is filled with a seething multimillion-degree plasma and crisscrossed by the powerful gravitational fields of hundreds of neighbors. In this high-stakes arena, galaxies undergo dramatic changes, and by studying these processes, astronomers gain unparalleled insight into the life cycle of galaxies everywhere. These clusters act as natural laboratories, accelerating evolutionary processes that would take billions of years in isolation into observable, rapid-fire events. One of the most common and relentless forces shaping galaxies in these dense environments is a process known as ram pressure stripping. Imagine a galaxy rich with cold gas and dust, the raw material for forming new stars plunging at thousands of kilometers per second into the superheated intracluster medium that fills the space between galaxies in a cluster. This is like holding a handful of fine dust out of a car window at high speed. The wind forcefully rips the dust from your hand. For the galaxy, the wind is the hot plasma, and it acts with immense force, stripping away the galaxy's precious reservoir of gas. This process effectively suffocates the galaxy, cutting off the fuel supply for new star birth. We see the evidence clearly in clusters like Norma. Spiral galaxies that have entered the cluster core have often lost their gas and appear quenched, their blue, star-forming arms fading as they transform into red, dead elliptical galaxies. This is a primary reason why the centers of rich clusters are dominated by these red and dead populations. Ram pressure stripping is a highly efficient mechanism for shutting down a galaxy's ability to create new stars. Alongside this gaseous assault, galaxies in clusters suffer from a more subtle but equally transformative phenomenon: galaxy harassment. This is not a single catastrophic event, but a death by 1,000 gravitational cuts. In the crowded core of a cluster, a galaxy will experience countless rapid, close encounters with other galaxies over billions of years. Each flyby exerts a strong tidal force, a gravitational tug that can stretch and distort the galaxy's structure. These repeated interactions can pull long streams of stars out into space, creating tidal tails, and they dramatically heat up the galaxy's stellar disk. A once orderly, flat spiral galaxy can have its stars stirred into a random, chaotic orbit, effectively puffing it up into a featureless, elliptical shape. Harassment is the primary reason why fragile spiral galaxies are rare in cluster centers, and it works in concert with ram pressure stripping to remodel a galaxy's appearance and internal dynamics from the inside out. The most dramatic events in these clusters, however, are the colossal mergers. While harassment involves quick flybys, a merger is a slow, gravitational dance that ends in a cosmic collision. When two large galaxies merge, it is one of the most energetic events in the universe. Their structures are utterly destroyed, and their stars are thrown into new, random orbits, creating a new, larger elliptical galaxy. These mergers also trigger intense bursts of star formation as clouds of gas collide and compress, and they can feed material onto the supermassive black holes at the galaxy's centers, igniting them as brilliant quasars. Within the Great Attractor, we see evidence of past mergers in the form of giant elliptical galaxies with multiple cores or vast shells of stars, the fossil records of ancient collisions. And the process is hierarchical. Small galaxy groups fall into the cluster, their own member galaxies merging first, before the resulting larger galaxy then merges with the cluster's central giant. This hierarchical merging is a fundamental driver of how galaxies, and the clusters themselves, grow in mass and size over cosmic time. By observing the diverse population of galaxies within the Great Attractor's clusters, from gas-rich spirals on the outskirts to quenched ellipticals at the core, astronomers can effectively watch cosmic evolution unfold in fast forward. The cluster provides a snapshot of galaxies at different stages of their transformation. This allows scientists to construct a detailed timeline of how environment dictates a galaxy's fate. The lessons learned in these extreme environments near the Great Attractor apply across the universe. The same physical processes occur wherever galaxies gather in groups, just at a slower, more gentle pace. Therefore, studying the violent metamorphosis within the heart of the attractor is not just about understanding one location. It is about decoding the universal rules that govern how all galaxies live, interact, and ultimately die, revealing the profound connection between the largest structures in the cosmos and the individual galaxies that inhabit them. Now, to truly map the Great Attractor's immense mass, especially the dark matter that makes up its bulk, we need to observe its most direct effect, its ability to bend the fabric of space-time itself. This brings us to one of the most powerful tools in modern cosmology, a technique that turns the universe into a giant lens. Gravitational lensing is a dramatic confirmation of Einstein's theory of general relativity, and it allows us to literally see the invisible by watching how light behaves as it travels through gravitational fields. The principle is elegant. Mass tells space-time how to curve, and curved space-time tells light how to move. The Great Attractor, with its colossal concentration of mass, acts as a monumental lens, distorting the images of galaxies that lie far behind it, and in doing so, it reveals its deepest secrets. This cosmic lensing manifests in two primary forms, each providing a different level of detail about the mass distribution. The first is strong gravitational lensing, which occurs when the alignment between a massive foreground object, a distant background galaxy, and our telescope is nearly perfect. In these rare and spectacular cases, the gravity of the foreground cluster is so intense that it can bend the light from the single background galaxy into multiple, distinct images, often stretched into brilliant arcs and rings that encircle the cluster's core. It's like looking at a distant street lamp through the bottom of a wine glass. The light is distorted into a complex pattern. In the heart of the Great Attractor region, around the dense Norma cluster, astronomers have observed these dramatic arcs. They serve as unmistakable proof of the tremendous mass present, acting as a natural magnifying glass that can sometimes amplify the light of incredibly distant objects, allowing us to see further back in time than we normally could. However, such perfect alignments for strong lensing are uncommon. For a comprehensive map of the entire Great Attractor complex, which spans hundreds of millions of light-years, astronomers rely on a more subtle but ubiquitous technique, weak gravitational lensing. Here, the distortions are far more gentle. Instead of creating multiple images or bright arcs, the gravity of the Great Attractor's widespread dark matter halo imposes a coherent, slight shearing effect on the shapes of millions of background galaxies. Imagine a distant galaxy that is intrinsically round. As its light passes through the gravitational field of the attractor, its image might be stretched ever so slightly into an elliptical shape. The distortion for any single galaxy is tiny, often indistinguishable from its natural irregular shape. But by measuring the shapes of tens of thousands of these background galaxies across a wide field of view, a consistent pattern emerges. Statistically, the average ellipticity of these galaxies will point toward the center of the mass causing the distortion. It's a monumental exercise in statistics, requiring deep, wide-field images from powerful telescopes like the Hubble Space Telescope or the Subaru Telescope, but the result is a breathtaking map of the total mass distribution, both seen and unseen. The process of creating this map is a feat of computational power. Astronomers start with a deep image of the sky in the direction of the Great Attractor, counting and measuring the shapes of countless faint, distant galaxies. Advanced computer algorithms then analyze the subtle alignments of these galaxies. Where the dark matter is most concentrated, the shearing effect will be strongest, and the galaxies will appear to be stretched in a direction tangential to the center of that mass concentration. By meticulously charting these minute distortions across the sky, scientists can reconstruct a three-dimensional map of the gravitational potential. This map doesn't show stars or gas, it shows the scaffolding of dark matter itself. When this weak lensing map is overlaid with the positions of the visible galaxies and the X-ray glow of hot gas, a complete picture emerges. The visible matter sits precisely at the peaks of the dark matter distribution, confirming that dark matter forms the underlying skeleton upon which the luminous universe is built. The power of gravitational lensing, especially the weak lensing technique, is that it is immune to the zone of avoidance. While dust in our own galaxy blocks the visible light from the Great Attractor, it does not block its gravity. The lensing effect operates on the light from galaxies far beyond the attractor, galaxies whose light travels over the dusty plane of the Milky Way on its way to us. This makes lensing the ultimate tool for peering through our own cosmic backyard to weigh the hidden giant. The resulting mass maps have been unequivocal. They show that the Great Attractor's gravitational influence is not confined to the bright core of the Norma cluster. Instead, it extends along the vast filaments of the cosmic web, revealing that the dark matter forms an extensive, interconnected network. The Great Attractor is not an isolated mass. It is the most pronounced knot in a dark matter web that governs the motion of our entire local universe, and gravitational lensing provides the definitive, direct evidence of its overwhelming gravitational presence. Yet, to truly see the Great Attractor in its entirety, we had to learn to observe it not with one type of vision, but with many. Each part of the electromagnetic spectrum, from long radio waves to energetic gamma rays, acts like a different filter on a camera, revealing a unique layer of this cosmic giant. It's as if we were trying to understand a vast, bustling city at night. Looking with our eyes alone, we might only see the bright lights of downtown. But by switching to thermal goggles, we'd see the heat radiating from buildings and power lines. Using radio scanners, we could listen to the conversations and traffic flows. Each different sensor unveils a new dimension of the city's activity. In exactly the same way, multi-wavelength astronomy allows us to compile a complete portrait of the Great Attractor, transforming it from a gravitational phantom into a richly detailed cosmic structure. Our journey across the spectrum begins with radio waves, the long wavelength workhorses that first pierced the zone of avoidance. Radio telescopes, tuned to the specific 21-centimeter wavelength emitted by neutral hydrogen gas, performed a kind of cosmic echolocation. This radiation passes effortlessly through the dust clouds of our own galaxy, allowing astronomers to detect and map the vast reservoirs of cold gas within the thousands of galaxies hidden behind the Milky Way's disk. This was the first major breakthrough, revealing the sheer number of galaxies congregating in the attractor region. But radio observations revealed more than just galaxies. They also detected the synchrotron radiation emitted by high-energy electrons spiraling around magnetic fields, often found in the lobes of active galactic nuclei. These radio-bright galaxies signaled the presence of supermassive black holes, adding another piece to the puzzle of the region's immense energy output and dynamic activity. Next, we shift to the infrared part of the spectrum. If radio waves are like listening, infrared light is like using night vision goggles. With longer wavelengths than visible light, infrared radiation can penetrate thick cosmic dust that would otherwise block our view. Space-based observatories like the Spitzer Space Telescope and the Wide-Field Infrared Survey Explorer gazed toward the Great Attractor and saw through the obscuration as if it were a thin fog. What they revealed was a stunning density of stars. Infrared light is excellent for tracing the distribution of older, cooler stars, which make up the bulk of a galaxy's mass. This provided a much more accurate census of the stellar mass in the region, confirming that the Great Attractor was not just a collection of gas-rich galaxies, but also a massive congregation of stellar bodies. Furthermore, infrared observations are superb for spotting dust-obscured star formation, revealing nurseries of new stars hidden within dense gas clouds that are completely invisible to optical telescopes. When we move to higher energies, the X-ray view is perhaps the most dramatic. This is where we see the violent, high-energy side of the Great Attractor. X-ray telescopes like Chandra and XMM Newton don't see starlight. They detect the glow of gas heated to tens of millions of degrees. Pointing these instruments at the Norma cluster, the heart of the attractor, unveiled a brilliant, diffuse halo of X-ray emission. This is the signature of the intracluster medium, the superheated plasma that fills the space between galaxies. The intensity of this glow allowed scientists to precisely weigh the gigantic reservoir of ordinary matter in the cluster and, by extension, calculate the total gravitational mass needed to contain such a hot, energetic atmosphere. X-rays also pinpoint the locations of ultra-hot gas being compressed in collisions between galaxy clusters and the intense radiation from matter accreting onto supermassive black holes, highlighting the most energetic processes shaping the region. At the very highest end of the spectrum, gamma-ray observations offer a glimpse of the most extreme phenomena. Gamma rays are produced by the most powerful events in the universe, such as the eruptions of active galactic nuclei or the annihilations of certain theoretical dark matter particles. While the Great Attractor is not a dominant source of gamma rays, observatories like the Fermi Gamma Ray Space Telescope have scanned the region. The relative quiet in gamma rays is actually informative. It tells us that while the attractor is gravitationally dominant, it is not currently host to an overwhelming number of the universe's most violent explosions. This multi-wavelength portrait from the calm, cold gas mapped by radio waves to the seething plasma seen in X-rays gives us a holistic understanding. It shows that the Great Attractor's power comes not from a single cataclysmic source, but from the combined complex interplay of billions of stars, vast clouds of gas, dark matter, and the relentless, transformative force of gravity working on an immense scale. Surrounding the immense gravitational concentration of the Great Attractor, and indeed woven throughout the entire cosmic web, are the universe's other dominant features, the cosmic voids. These are not merely empty spaces between the glittering filaments and clusters. They are vast, dynamic regions that play an absolutely critical role in shaping the cosmos. If the Great Attractor is a deep gravitational valley, then these voids are the towering mountains, and their profound emptiness is just as influential as any concentration of mass. The very existence of these voids and their behavior is key to understanding the full picture of our cosmic motion and the ultimate fate of large-scale structure. The scale of these voids is almost impossible to grasp. They are not small bubbles but colossal spherical or irregular regions that can span hundreds of millions of light-years across. To put this in perspective, if our Milky Way galaxy were the size of a grain of sand, a typical cosmic void would be an empty sphere larger than the entire Earth. The local void, a region that borders our own local group of galaxies, is one such example, exerting a subtle but significant push on us by virtue of its lack of pull. Within these voids, the density of galaxies is drastically lower than the cosmic average. You might find a few isolated dwarf galaxies or small, faint groups, but the great cities of stars found in clusters are entirely absent. This extreme underdensity creates a gravitational landscape of profound imbalance, which is the primary engine behind their cosmic significance. The physics of how these voids evolve is fascinating and counterintuitive. While gravity is relentlessly pulling matter into the dense filaments and clusters, causing them to contract, it is simultaneously causing the voids to expand. Here's how it works. Imagine a region of space that starts off only slightly emptier than its surroundings. Because it has less mass, its gravitational pull is weaker. The surrounding, denser regions have stronger gravity and thus pull matter away from the underdense void. This makes the void even emptier, further reducing its gravitational pull, which in turn allows it to expand relative to the denser regions around it. It's a runaway process. The boundaries of the void act like a watershed, with all the matter flowing outward, away from the emptiness and toward the gravitational attractors. This means that over billions of years, the voids grow larger and emptier, while the filaments and clusters grow denser and more massive. This differential expansion has a profound connection to the mysterious force of dark energy. Because voids are so empty, the expansion of the universe within them is less hampered by the local gravitational tug of matter. As a result, the space inside a void actually expands faster than the space within a dense cluster. In a sense, the voids are the places where dark energy first gains a foothold and begins to dominate. They are the vanguard of the accelerating universe. As time goes on and dark energy's influence strengthens, these voids will continue to grow, their boundaries stretching and the filaments of the cosmic web that separate them becoming ever more tenuous. The voids are not passive bystanders in the cosmos. They are active participants whose expansion is steadily reshaping the architecture of the universe. The significance of cosmic voids, therefore, extends far beyond their emptiness. They are essential for defining the very structure of the cosmic web. You cannot have a web without holes. The voids provide the negative space that gives the filaments their form. They act as the gravitational hills from which galaxies slide down into the valleys of the Great Attractor. Our own motion is a direct consequence of this topography. We are being pushed away from the underdense local void as much as we are being pulled toward the overdense attractor. By studying the sizes, shapes, and distribution of these voids, cosmologists can test fundamental theories about the nature of dark matter and dark energy. The pattern of voids is a fossil record of the initial conditions of the universe, and their growth over time is a direct measure of the competing forces of gravity and cosmic expansion. In the grand narrative of the cosmos, the great emptiness of the voids is as eloquent as the brilliant light of the clusters, telling the parallel story of how the universe is being pulled apart even as it is being drawn together. So we've explored the immense gravitational currents and the vast cosmic web, but where does our journey ultimately lead? To answer that, we need to introduce the true scale of our home, the continent of galaxies we belong to. This is the Laniakea supercluster, and the Great Attractor is not merely a feature within it. It is its beating heart, the gravitational anchor around which our entire local universe revolves. Defining a supercluster is a more subtle task than it might seem. A galaxy cluster is a clearly bound object with galaxies orbiting a common center. But a supercluster is something far more vast and dynamic. It's not a single, tightly knit structure, but a collection of thousands of galaxies, groups, and clusters that share a common destiny, all flowing together within the same gravitational watershed. For decades, we thought our address was the Virgo supercluster, with the Virgo cluster as its center. But that was a misconception based on a simple map of locations. The revolutionary insight came when astronomers realized that to find our true home, they couldn't just look at where galaxies are, they had to watch how they move. The groundbreaking study that redefined our cosmic neighborhood was led by astronomer R. Brent Tully and his team in 2014. Their method was elegant yet powerful. Instead of relying solely on the positions of galaxies, they meticulously mapped the peculiar velocities, the real, physical motions of galaxies after subtracting the uniform expansion of the universe. This was like being able to see not just the rafts on a wide river, but the direction and speed of the currents beneath them. By tracing these flow lines, they could see a coherent pattern emerge across the cosmos. Thousands of galaxies, including our own Milky Way, were all streaming along invisible gravitational channels toward a single, common destination, the Great Attractor. This map of cosmic flows revealed the true boundaries of Laniakea. The name from Hawaiian means immeasurable heaven, and it is a fitting title for a structure spanning over 500 million light-years. Its borders are not walls of galaxies but rather gravitational divides, like continental divides on Earth where rainfall flows toward different oceans. The edge of Laniakea is defined by the points where the flow of galaxies changes direction, no longer heading toward our Great Attractor but instead turning toward a different gravitational center, like the neighboring Perseus-Pisces supercluster or the immense pull of the Shapley supercluster far beyond. Within this immense volume, every galaxy is part of the same river system, all destined to eventually flow toward the central gravitational valley. This redefinition demoted our previous home, the Virgo supercluster, to a mere appendage of Laniakea. The Virgo cluster is now understood as a significant nearby mass concentration that influences us locally, but it is itself falling along with us toward the far more powerful Great Attractor. Imagine Laniakea as a vast river basin. The Great Attractor is the lowest point, the lake into which all the rivers drain. Our local group of galaxies is like a small creek on the very outskirts of this basin, and the Virgo cluster is a larger tributary that our creek flows into before joining the main river. We are connected to Virgo, but our ultimate destination is determined by the geography of the entire continent, not just the local tributary. Understanding Laniakea transforms the Great Attractor from a mysterious, isolated force into its proper role, the central node of our local cosmic ecosystem. It is the focal point where the largest filaments of the web in our vicinity converge. This perspective solves the long-standing puzzle of why such a powerful gravitational anomaly exists. It's not an aberration, it is a natural and expected consequence of the hierarchical way the universe builds structure. The dark matter scaffolding that underlies Laniakea naturally developed a deepest point, a gravitational well that has been gathering matter for billions of years. The Great Attractor is that well, and its immense pull is simply the collective gravity of the entire supercluster acting in concert. Our cosmic address is no longer just a set of coordinates. It is a dynamic position within a flowing river of galaxies, all guided by the silent, relentless pull of the heart of Laniakea. But for all the incredible progress we have made, the story of the Great Attractor is far from complete. Peering through the zone of avoidance and mapping the cosmic flows with existing technology has been like trying to decipher a faded, ancient manuscript with a dim candle. We have grasped the main narrative, but countless details, subtle nuances, and perhaps even entire chapters remain hidden. The next great leap in our understanding will come from a new generation of astronomical observatories, instruments of such breathtaking power and sensitivity that they promise to transform our view from a blurry sketch into an ultra-high-definition movie. These are not mere incremental upgrades, they are revolutionary tools designed to probe the deepest secrets of dark matter, dark energy, and the large-scale structure of the universe, with the Great Attractor serving as a primary testing ground. Leading this charge is the James Webb Space Telescope, an observatory that has already captivated the world with its stunning images. While Webb is often celebrated for its ability to see the universe's first galaxies, its infrared vision is perfectly suited for a critical task closer to home, conducting a deep census of the Great Attractor region. Remember, infrared light slips through cosmic dust with ease. Webb can stare directly through the heart of the Milky Way's zone of avoidance, not just to find the galaxies we know are there, but to study them in exquisite detail. It can analyze the stellar populations of galaxies within the Norma cluster, determining their ages and compositions to reconstruct the cluster's violent merger history. It can peer into the dusty nurseries of newborn stars within these galaxies, understanding how the extreme cluster environment affects star formation. Most importantly, Webb's powerful spectrographs can measure the velocities of individual stars within these distant galaxies with unprecedented precision, allowing us to map the gravitational field of the Great Attractor with a fineness we never thought possible, effectively weighing the dark matter distribution star by star. While Webb provides the deep, focused view, the European Space Agency's Euclid mission offers a panoramic perspective of almost unimaginable scope. Euclid is a cosmology machine designed specifically to tackle the mystery of dark energy and dark matter by mapping the geometry of the cosmic web across 10 billion years of cosmic history. Its wide-field camera will survey a vast portion of the sky, capturing the light from billions of galaxies. For the Great Attractor, this means Euclid will provide a definitive map of the entire Laniakea supercluster and its surroundings, charting the filaments and voids with a clarity that will make our current maps look like rough sketches. But Euclid's true power lies in its ability to perform weak gravitational lensing on a colossal scale. By measuring the subtle distortions in the shapes of countless distant galaxies, Euclid will create the most detailed map ever made of the dark matter distribution in our local universe. It will show us the invisible skeleton of the Great Attractor in stunning detail, revealing how the dark matter filaments connected to other superclusters and precisely quantifying the total mass that has been pulling on us for eons. On the ground, a different kind of revolution is brewing with the development of the Square Kilometre Array, or SCAR. This is not a single telescope but a vast network of radio antennae spread across 2 continents, Australia and South Africa. When completed, it will have a total collecting area of over 1 square kilometre, making it the most sensitive radio telescope in history. The SKA's capabilities for studying the Great Attractor are almost science fiction-like. It will be able to detect the 21-centimeter emission from neutral hydrogen gas in galaxies so faint and distant that they are currently invisible to us. This will allow it to map the cosmic web in incredible detail, tracing the faintest, most tenuous filaments of gas that feed the Great Attractor. Furthermore, by observing these hydrogen signals, the SKA can measure the rotation of galaxies with exquisite accuracy, providing an independent and highly precise measurement of their velocities. This will enable scientists to create a dynamic, 3-dimensional model of the bulk flows in our local universe, watching the real-time motion of galaxies as they stream toward the attractor and potentially uncovering smaller flows and structures that are currently beyond our detection. The synergy between these missions will be their greatest strength. Webb's detailed infrared views of individual galaxies will provide the ground truth for Euclid's wide-field dark matter maps. The SKA's unparalleled hydrogen surveys will reveal the gas content and precise velocities that complement both. Together, they will act as a single, multi-wavelength observatory of unprecedented power. They will allow us to test whether our standard model of cosmology, lambda-cold dark matter, holds up in our own cosmic backyard. Do the motions of galaxies around the Great Attractor precisely match the predictions of our models? Is dark matter behaving exactly as we think it should on these vast scales? Any tiny discrepancy could point toward new physics, perhaps a subtle modification to gravity or a new property of dark matter itself. The Great Attractor, once a frustrating anomaly, is now poised to become a benchmark, a cosmic laboratory where our most fundamental theories about the universe are put to the test by the most advanced technology humanity has ever built. Despite the compelling evidence for dark matter shaping the Great Attractor, the sheer strangeness of this invisible substance has led some scientists to propose a radically different solution. What if the anomaly isn't caused by unseen mass, but by a flaw in our understanding of gravity itself? This idea forms the core of a class of theories known as modified Newtonian dynamics, or MN. Instead of inventing a new, mysterious particle, MN suggests that Isaac Newton's law of gravity, while excellent for predicting the orbits of planets, breaks down in environments where gravity is incredibly weak, such as the outer regions of galaxies or the vast spaces between clusters. In these extreme low acceleration regimes, gravity might become slightly stronger than Newton or Einstein predicted, eliminating the need for dark matter to explain the observed motions. The appeal of MUND is its elegant simplicity. It was originally proposed to explain the rotation curves of individual galaxies without dark matter, and it succeeded remarkably well. Proponents argue that applying a modified version of gravity to the large-scale structure could similarly account for the peculiar velocities of galaxies flowing toward the Great Attractor. In this view, the attraction isn't a hidden mass but a natural consequence of gravity behaving differently over the immense, sparse distances of the cosmic web. The collective pull of the visible galaxies and gas, when calculated with modified equations, might be sufficient to generate the observed flow. This challenges the very foundation of the standard cosmological model, suggesting we might be misinterpreting the universe's dynamics based on an incomplete law. However, the modified gravity hypothesis faces significant hurdles when confronted with the full suite of evidence. While it might explain galactic motions, it struggles to account for other independent observations that point decisively toward dark matter's existence. For instance, the phenomenon of gravitational lensing provides a direct measure of total mass. The way the Great Attractor bends the light from distant galaxies indicates a concentration of mass far exceeding what is visible, and this lensing effect is a pure consequence of general relativity's description of gravity warping space-time. Modifying gravity to explain one set of observations often makes it difficult to explain this other, crucial piece of the puzzle simultaneously. Furthermore, the detailed structure of the cosmic microwave background, with its specific pattern of hot and cold spots, is exquisitely well fit by a model that includes dark matter. Reproducing this precise pattern with a modified gravity theory has proven to be a monumental challenge. This has led to an ongoing and spirited debate within the astrophysics community. On one side, proponents of the Standard Model argue that the evidence is overwhelming. The coherent picture formed by galaxy motions, gravitational lensing, the CMB, and the distribution of hot gas in clusters all converges on the same answer. Dark matter is real, and it is the primary architect of structures like the Great Attractor. They see MAND as an ad hoc fix that solves one problem while creating several others. On the other side, critics maintain that the dark matter hypothesis has its own issues, notably the decades-long failure to directly detect a single dark matter particle here on Earth despite numerous sophisticated experiments. They argue that this continued lack of direct evidence keeps the door open for more radical explanations. The controversy extends beyond a simple binary choice. Some researchers are exploring hybrid models that incorporate elements of both ideas, perhaps involving a subtle modification to gravity alongside a new type of dark matter particle. The Great Attractor, with its complex gravitational field and its position as a major node in the cosmic web, serves as a crucial testing ground for these competing ideas. Precise measurements of the bulk flow of galaxies on these immense scales can, in theory, distinguish between the predictions of the Standard Model and various modified gravity theories. As new data pours in from observatories like the James Webb Space Telescope and the Euclid mission, the subtle motions of galaxies within the Laniakea supercluster will be scrutinized like never before. The ultimate resolution of this debate will not come from proving one side entirely right, but from which framework can most naturally and completely explain all the observations, from the spin of a single galaxy to the flow of thousands toward a mysterious hidden heart. The Great Attractor, therefore, remains more than just a destination. It is a cosmic courtroom where our most fundamental theories about the force that shapes the universe are being put on trial. To truly grasp the significance of the Great Attractor, we need to step into a time machine and witness its entire life story, from the faintest whisper in the newborn universe to the colossal structure we observe today. Its timeline begins not with a bang, but with a whisper, an infinitesimal quantum fluctuation in the first fleeting moment after the Big Bang. During the period of rapid inflation, that subatomic ripple was stretched to a cosmic scale, creating a region of space that was ever so slightly denser than its surroundings. This tiny overdensity, a mere 1 part in 100,000, was the seed from which the entire Laniakea supercluster would eventually grow. For hundreds of thousands of years, this seed lay dormant as the intense pressure from the hot, dense plasma of the early universe prevented gravity from doing its work. The universe was simply too hot and energetic for structures to begin collapsing. The turning point arrived around 380,000 years after the Big Bang, at the epoch of recombination. As the universe cooled enough for neutral atoms to form, it became transparent, and the cosmic microwave background radiation was released. With the radiation pressure suddenly gone, gravity was finally unleashed. The slightly denser region that would become the Great Attractor began to exert a stronger gravitational pull than its surroundings. Dark matter, which had already begun to clump together unaffected by radiation, started to form an invisible scaffolding. Ordinary matter, the hydrogen and helium gas, then flowed into this pre-existing dark matter framework. For the first billion years, this region grew slowly, steadily accumulating mass while the first stars and galaxies flickered to life across the cosmos. The real era of dramatic growth for the Great Attractor occurred over the next several billion years, during the universe's most active period of structure formation. This was a time of immense cosmic construction, driven by the hierarchical merging of smaller structures. Think of it as a vast river system forming. First, tiny streams of gas and dwarf galaxies merged to form larger galaxies. Those galaxies then gathered into small groups. The gravitational pull of the growing attractor region began to draw in these groups and filaments from millions of light years away. It acted as a gravitational sink, a focal point in the emerging cosmic web. Galaxy clusters like the Norma cluster that would become its heart began to assemble through violent mergers, their immense gravity pulling in ever more gas and galaxies. By the time the universe was about half its current age, the Great Attractor had already become the dominant gravitational force in our local cosmic volume, establishing the flow patterns that would eventually guide our own Milky Way. Today, 13.8 billion years after the Big Bang, the Great Attractor is a mature structure, but its evolution is far from over. We are currently in an era where gravity still dominates locally within superclusters like Laniakea. Our galaxy and thousands of others continue to flow along the cosmic filaments toward this gravitational center. However, the future of the Great Attractor is not one of continued growth and consolidation. A countervailing force has entered the cosmic equation, dark energy. This mysterious energy inherent to space itself is causing the expansion of the universe to accelerate. For the next tens of billions of years, gravity will continue to rule within the local web. The Great Attractor will likely merge with other nearby clusters, growing even more massive. Our local group may eventually reach a point of closest approach, coming within a few 100 million light-years of this cosmic hub. But in the truly far future, dark energy will ultimately prevail. As the expansion of space accelerates, the gravitational bonds that hold superclusters together will be stretched and eventually severed. The filaments of the cosmic web that feed the Great Attractor will thin out and snap. Galaxies that are currently flowing toward it will find their motion reversed, not by a repulsive force, but by the expansion of the space between them. The Great Attractor, and indeed the entire Laniakea supercluster, will be pulled apart. The galaxies within it will become increasingly isolated, their collective identity lost to the void. In a future universe trillions of years from now, the Great Attractor will be no more, its constituent galaxies receding from one another into an ever-darkening and empty cosmos. Its story, from a quantum seed to a gravitational titan to a dissolved memory, mirrors the grand narrative of the universe itself, a cycle of assembly and dissolution on the most epic scales imaginable. This journey to understand the Great Attractor does not exist in a vacuum. It is intimately woven into the fabric of other, even grander cosmic mysteries. Unraveling its secrets is not a final destination but a critical pathway toward answering the most profound questions we can ask about the cosmos. The forces that sculpted the Great Attractor are the same forces that govern the entire universe, from its birth in the Big Bang to its ultimate fate. By studying this one gravitational anomaly, we are effectively conducting a local experiment that has implications for the entire cosmos, connecting the dots between the largest structures we can see and the most elusive components of reality. Perhaps the most direct connection is to the enigma of dark energy. Our understanding of the Great Attractor's future is entirely dependent on this mysterious force. We've seen how the competition between gravity's relentless pull and dark energy's repulsive push will determine whether we ever truly join the attractor or are carried away by the accelerating expansion of space. But the relationship is deeper than just a future prediction. The precise way that galaxies flow toward the Great Attractor, their peculiar velocities, serves as a sensitive probe for measuring the strength of dark energy's influence right now. If the observed bulk flows in our local universe are stronger or weaker than what our standard cosmological models predict, it could indicate that dark energy is not a constant force, as represented by Einstein's cosmological constant, but something that varies over time. A tiny discrepancy in the motion of galaxies within Laniakea could be the first clue that our understanding of dark energy is incomplete, forcing a revision of our ideas about the universe's ultimate destiny. The Great Attractor also provides a crucial bridge back to the universe's infancy, to the epoch of inflation. The initial density fluctuation that seeded this vast supercluster was one of the quantum ripples stretched to cosmic proportions during that first fraction of a second. By meticulously measuring the final, evolved structure of the attractor, its total mass, its shape, its position in the web, cosmologists can work backwards. They can test the predictions of different inflationary models. Did inflation happen exactly as we think? Did it produce the specific kind and distribution of seeds that would naturally grow into a structure like Laniakea? The detailed map of the dark matter distribution within the attractor, revealed through gravitational lensing, is a fossil record of those initial conditions. It allows us to peer back in time, using the largest structures of the present day to interrogate the very first moments of existence. Furthermore, the story of the Great Attractor is inextricably linked to the long-standing mystery of the universe's missing baryons. We know that ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and us, accounts for only a small percentage of the universe's content. Yet for years, astronomers could not account for all of this ordinary matter that theories said should have been created in the Big Bang. A significant portion was simply missing. The discovery of the colossal reservoir of superhot gas within the Great Attractor's core was a major piece of this puzzle. It showed that a huge fraction of the universe's ordinary matter exists not in galaxies, but in these vast, diffuse clouds of plasma trapped in gravitational wells. Solving the mystery of the Great Attractor contributed directly to solving the missing baryon problem, demonstrating how investigating one cosmic anomaly can shed light on a completely different, yet fundamentally connected issue. This interconnectedness reveals a beautiful truth about cosmology. The universe is not a collection of separate puzzles, but a single, complex system. The Great Attractor is a focal point where multiple threads of inquiry converge. Understanding its dark matter content informs the search for dark matter particles. Charting its influence on galactic motions tests our theories of gravity on the largest scales. Studying the violent evolution of galaxies within its heart teaches us about the life cycle of all galaxies. There is no clean separation between these mysteries. They are different facets of the same grand narrative. The Great Attractor acts as a cosmic crossroads, a place where the mysteries of dark matter, dark energy, cosmic structure formation, and galactic evolution all meet. By continuing to study this immense gravitational heart, we are not just learning about our local neighborhood. We are reading a chapter in the universal story that binds the smallest quantum fluctuations to the largest scales of space and time, bringing us closer to a complete picture of the cosmos we call home. And so, after this incredible journey through 30 secrets, from a subtle deviation in galactic motion to the vast expanse of the Laniakea supercluster, we arrive at the ultimate question. What does the Great Attractor, this grand gravitational heart, truly reveal about the fundamental nature of our universe? Its story is far more than a localized mystery solved. It is a powerful lens through which we can read the cosmic rulebook, a single, magnificent case study that illuminates the deepest principles governing all of existence on the largest scales. First and foremost, the Great Attractor is a masterclass in cosmic structure formation. It stands as a triumphant validation of our leading model of the universe, the lambda-cold dark matter model. This structure did not appear by chance. Its existence and specific properties were essentially preordained by the tiny quantum fluctuations imprinted during the inflationary Big Bang, and then meticulously sculpted over billions of years by the relentless force of gravity. The attractor shows us that the universe builds itself hierarchically from the bottom up. Small structures merge to form larger ones, with dark matter acting as the invisible scaffolding that guides ordinary matter into the magnificent cosmic web of filaments, nodes, and voids. The precise way galaxies flow along these filaments toward the Great Attractor matches the predictions of supercomputer simulations with stunning accuracy, confirming that we understand the basic recipe for building a universe. It is a living fossil, a preserved record of cosmic evolution that allows us to witness the outcome of processes that began 13.8 billion years ago. Furthermore, the Great Attractor provides perhaps the most compelling local evidence for the composition of the cosmos. Its immense gravitational pull, which cannot be accounted for by visible matter alone, is direct, observable proof of dark matter's dominance. But its story doesn't end there. The eventual fate of the attractor, the fact that the accelerating expansion of the universe will ultimately tear apart the Laniakea supercluster, ties it directly to the mystery of dark energy. This one structure, therefore, encapsulates the entire cosmic budget, a universe made of about 5% ordinary matter, 27% dark matter, and 68% dark energy. It is a physical manifestation of the cosmic struggle between these components. Gravity, embodied by dark matter, works to pull the universe together, creating intricate structure. Dark energy works to push it apart, ultimately leading to isolation. The Great Attractor exists in the brief cosmic epoch where gravity still rules locally, allowing us to study its effects in exquisite detail before dark energy wins the long-term battle. On a more profound level, the investigation of the Great Attractor has reshaped the very process of scientific discovery, teaching us a crucial lesson about our own perspective. For years, the solution was hidden in our blind spot, the zone of avoidance. This forced astronomers to innovate, to develop new ways of seeing that moved beyond traditional optical astronomy. The successful mapping of the attractor using radio waves, infrared light, X-rays, and gravitational lensing heralded a new era of multi-messenger astronomy. It demonstrated that to understand the cosmos, we cannot rely on a single sense. We must listen to the universe across the entire electromagnetic spectrum and even observe its subtle distortions of space-time. This approach has now become standard practice, fundamentally changing how we explore other cosmic mysteries. The Great Attractor taught us humility, showing that the truth can be concealed by our own vantage point, and it rewarded that humility with a revolutionary expansion of our observational toolkit. Ultimately, the greatest revelation of the Great Attractor is one of connection. It dissolves the illusion of our isolation. We are not a lone galaxy drifting passively through an empty void. We are participants in a dynamic, flowing river of galaxies, caught in a gravitational current that connects us to thousands of our celestial neighbors. Our motion is not random. It is a direct response to the largest structures in our universe, structures built from the faintest echoes of its birth. The force that guides our Milky Way is the same force that shaped the cosmos, governed by laws that we are only beginning to comprehend. The Great Attractor, therefore, is more than a distant concentration of mass. It is a fundamental part of our cosmic identity, a constant reminder that we are embedded in a grand, evolving tapestry whose patterns reveal the deepest secrets of space, time, and existence itself. Despite the breathtaking progress we have made in mapping its influence and understanding its place in the cosmic web, The Great Attractor remains at its core an enigma that continues to challenge the very frontiers of cosmology. For every question we answer, two more seem to emerge from the depths of interstellar space. One of the most profound, unresolved puzzles is the precise nature of the dark matter that constitutes its overwhelming mass. We can map its gravitational shadow with incredible precision, but we still have no idea what this mysterious substance actually is. Is it a sea of undiscovered subatomic particles, as most physicists believe? Or does its ghostly influence point toward something even more exotic, perhaps a modification to the fundamental laws of gravity on cosmic scales? The Great Attractor is the ultimate natural laboratory for this investigation, but until we can directly detect or create dark matter, its true identity remains one of the universe's best-kept secrets. Our view is also still frustratingly obscured. While we have cleverly pierced the zone of avoidance with radio and infrared eyes, our maps of the region directly behind the densest part of the Milky Way's galactic bulge are still incomplete and blurry. It is entirely possible that significant structures, additional galaxy clusters, or vast clouds of gas remain hidden within this deepest part of our blind spot, subtly altering the gravitational calculations we use to explain our motion. Imagine trying to predict the weather for a continent while a massive mountain range blocks your view of an entire ocean. You might understand the general patterns, but a major storm system could be developing just out of sight. Current and future surveys will continue to chip away at this obscuration, but the possibility of a hidden gravitational surprise lurking behind the Milky Way is a tantalizing and humbling reminder of our limited perspective. Theoretical models, powerful as they are, also face significant challenges when applied to a structure of this complexity. Supercomputer simulations of the cosmos can reproduce the large-scale web with remarkable fidelity, but they often struggle to accurately predict the precise velocities and distributions of galaxies within a specific supercluster like Laniakea. The detailed dynamics of how thousands of galaxies flow along the cosmic filaments, how they interact with each other, and how they eventually settle into the gravitational basin of the attractor involve a level of intricate physics that is incredibly difficult to simulate. Tiny discrepancies between the predicted and observed bulk flows could be mere statistical noise, or they could be the first hints of new physics, perhaps a subtle property of dark matter or a slight deviation in the behavior of gravity over immense distances. The Great Attractor serves as a stringent test for our models, and its refusal to perfectly conform to our expectations is what keeps theoretical cosmologists awake at night, refining their equations in search of a more complete picture. This enduring mystery is precisely what fuels the next generation of astronomical exploration. The unanswered questions are not a sign of failure but a beacon guiding future research. The fact that the Great Attractor continues to challenge us is a testament to its fundamental importance. It is not a problem to be solved and filed away. It is a permanent feature of our cosmic landscape that will serve as a benchmark for centuries to come. As our technology evolves, so too will the nature of the questions we can ask. We are moving from simply asking, "What is it?" to far more nuanced inquiries about its detailed formation history, its role in the galactic life cycle, and its ultimate fate in an accelerating universe. The Great Attractor, in its silent gravitational dominance, continues to be a source of profound inspiration, a constant reminder that the universe is far stranger and more wonderful than we can imagine, and that the greatest discoveries often lie not in the answers we find, but in the new mysteries those answers reveal. Our journey through these 30 secrets has taken us from a subtle anomaly in galactic motion to the very frontiers of cosmic understanding. We've witnessed how a mysterious gravitational pull led us to uncover a hidden continent of galaxies, the Laniakea supercluster, with the Great Attractor as its beating heart. We've learned to see with more than just our eyes, using radio waves to pierce the zone of avoidance, X-rays to reveal seething oceans of hot gas, and gravitational lensing to map the invisible dark matter skeleton that shapes our cosmic destiny. The story of the Great Attractor is not the tale of a single monstrous object, but a profound lesson in the architecture of the universe itself. These discoveries represent a fundamental shift in our cosmic perspective. We are no longer isolated inhabitants of a lone galaxy, but active participants in a dynamic, flowing river of stars, caught in a gravitational current that connects us to thousands of celestial neighbors. Our place in the cosmos has been redefined from the center of a small local group to a tiny suburb on the outskirts of an immense heaven. This humbling realization is also an empowering one. It demonstrates the incredible power of human curiosity and ingenuity, our ability to decipher the universe's deepest laws by carefully observing the silent, relentless pull of gravity across billions of light years. The journey, however, is far from over. The Great Attractor remains a source of deep mystery. The true nature of the dark matter that gives it power is still unknown. The precise balance between its gravitational pull and the repulsive force of dark energy will dictate the ultimate fate of our entire supercluster. With every question we answer, new and more fascinating puzzles emerge, waiting for the next generation of telescopes and the next great leap in human understanding. The universe is not a puzzle to be solved, but a story to be continued, with each chapter revealing greater wonders and more profound connections. And that story is one we are all a part of. The same forces that sculpted the Great Attractor from quantum whispers in the first moments of time have also shaped the world we live on and the atoms that make us who we are. To look up at the night sky and understand that we are flowing toward an immense gravitational heart is to feel a profound connection to the cosmos. It is an invitation to keep wondering, to keep exploring, and to keep asking the big questions. The secrets of the universe are there for the taking. What mysteries will we uncover next? Share your thoughts and questions in the comments below, and join us as we continue to explore the greatest story ever.